Testing one, two, testing one, two. Well, it's 1 o'clock. We're still waiting on our 1 o'clock presenter to arrive. Hopefully, she'll be here soon. But just hang tight and we'll get started as soon as they arrive. Hi, welcome.
All right, and then I just put present, correct? Okay.
All right, good afternoon, everyone. Welcome back to lunch. Hopefully, everyone was able to figure out that we were on a different link and you had to go on our YouTube channel to get it. But the numbers are increasing steadily, so I figure people are coming back from lunch. We're going to start our afternoon session of observing severe weather. There's 5 talks, all from Texas Tech University. It should be pretty sciencey if you like the science behind severe storms. And we'll start off with, is it Ely or Ellie? Ellie Ventiker, maybe?
Ventiker, yeah.
Okay, cool. And she's going to give a talk on observations of rear flank internal surges from the 2019 targeted observations by the TORUS project. So thank you, and go ahead.
All right. So as he said, I was looking at surges of the RFD within the TORUS data set from the previous year. So the motivation behind this project is basically, we typically, when we're forecasting severe storms, we think about these environmental factors like wind shear and CAPE and things like that. And while these are really good indicators of where supercells might occur and so forth, we still have a high false alarm rate. So obviously there's something happening at a smaller scale. So when you look at a storm, you have 2 areas. You have the forward flank and your rear flank, and then the updraft as well. And so when you only consider the updraft, which when you typically think about, your standard, you have wind going one direction and then wind going another direction, and then you have a rotating tube of air and it gets tilted by an updraft. Well, that's great and it helps you get a storm, but it really doesn't explain how you could get rotation near the surface, because as you're tilting that air, it's moving away from the surface. So by the time it becomes vertical, it's well away from your surface layer. But if you consider your RFD, which is the rear portion of the storm here, and your downdraft, you're tilting as you're moving towards the surface. And so you get that rotation near your boundary layer. Then if you look further at a smaller scale, at the RFD itself, you can see these features called rear flank internal surges, which are basically just areas where you have enhanced flow embedded within a larger RFD. And these have been observationally documented in several different cases. And interestingly, they have often been observed close to the time of tornadogenesis. And they have many different characteristics. Some are colder than the environment, are the RFD that they're embedded in. Some are warmer, some are quite long-lived, like 20 minutes. Some last a matter of, 4 minutes. So it's not a very well documented feature aside from a few isolated cases. But it's hypothesized that the reason why it might be related to tornadogenesis is, again, enhancing this near surface rotation. And it can do so by a couple ways. The first is the tilting and shearing and stretching. And that makes sense when you have more viscosity and you tilt it and stretch it. Our dynamics will tell us that that's going to enhance the vorticity experienced within your parcel. And so when you have more convergence and more tilting occurring along a boundary, which these features are, that can enhance your vorticity. Secondly, if you have a warmer surge, it might enhance your buoyancy. So enhancing your buoyancy makes it more likely to rise. More likely to rise means more of that stretching and tilting and more vorticity. So it all kind of feeds back on each other. So aside from its potential relationship to tornadogenesis, these features can be pretty damaging in their own right. So looking at the Tuscaloosa tornado, they found large swaths of damage outside of the path of the tornado itself. And so they looked at a couple different reasons why this could be, and they eventually decided that it was most likely due to a surge event or multiple surge events. So they can cause quite a bit of damage outside of their relationships to other storm features. So as I mentioned before, these have been observed in multiple different cases, but these are isolated case studies. There really has not been a longitudinal study across multiple storms about these features. So that means we have like several fundamental questions that are yet unanswered. How common are these surges? How long do they typically last? How big are they? Are they, do they occur in every supercell or only a small subset? We don't really know this. We don't even have a consensus name for what to call them. In the literature, they go by many different names, and I've listed just a few, but yeah. So that kind of leads me to my project. And my project is looking at data from TORUS, which is a collaborative field project we did. And Talk's going after me, or it's going to talk more about the broader aspects of that project. But it's multiple platforms, and so in multiple days. And it was over 2019, which, if any of you remember, was a quite active storm season. So we got pretty lucky in that we have multiple cases and multiple days to look at, which could allow for this longitudinal type study where we're just looking across multiple storms for these features. So my research plan, first I have to identify surge events. Then I have to figure out even what I'm defining as the surge event, since it hasn't been well established in the literature. And then finally, I'm going to be comparing and contrasting different surge events to each other, looking for common features, looking for ways that they could potentially relate to other storm features such as tornadogenesis. So my first step, so this is the cataloging step. This is basically evaluating the data and using all these different platforms that we used in the TORUS mission. So radars, mesonets for thermodynamic info, as well as drones and other features. So I've started doing this already for the KA data, which is a radar platform we have here at TTU. And I'm looking at things such as time and location of the surges, number of surges per storm, their theta E and theta V perturbations. And these two variables are chosen because of their relationship to buoyancy fluctuations, as well as other features such as whether or not they're related to a tornadogenesis case, so on and so forth. And so far, based on just the KA, I'm being very liberal about what I include. Like if it's potentially a surge case, it's going in the catalog, again, because we don't have a definition yet. So once we have all these, we can go back and start eliminating cases. So step 2, that's where we have to define a definition. So we do have one attempt at a definition in the literature, a concrete definition, and that's from Lee et al. 2012. And he says that it's a 13 meter per second or greater wind speed difference across the boundary. But that doesn't include thermal information, as well, which is an important factor of these phenomenon. And it's not commonly accepted. So it leaves quite a bit of room for us to define our own definition. And we'll probably end up with a threshold definition where we can look at kinematic, so radar data, how large our wind shifts are, and or our thermodynamic data if we have a nice in situ measurement. So step 3, going forward, we're going to compare these surge events. So again, we want to answer these fundamental questions. How common are surges? What are their typical characteristics? And then relating them to tornadogenesis and or enhancements in low-level vorticity, because we might not have enough tornadogenesis cases in our data set. And so in that regard, we have 3 potential hypotheses that we've noticed a trend in the data. Typically, when you have a surge that's related to tornadogenesis in the literature, it has been warmer than its embedded RFD, whereas cold surges can be related to tornadogenesis failure and or dissipation of the tornado, which again makes sense because you're enhancing your buoyancy. Is it a greater wind shift? So maybe stronger surges are more likely to cause the tornado because they're enhancing your convergence. And how large are they in a spatial XY sense? So perhaps if you have a smaller surge, it's forcing the convergence into a smaller area that might be more beneficial for your tornadogenesis. So I have 2 cases that I've looked at in depth. And the first is May 24th, 2019. And this was an HP supercell near Matador, Texas. And so the 2 images on the bottom here are RHI scans. And you can see, can people see my cursor if I move it around? Okay, so here is our surge boundary, which we'll step through and move forward with time. And here is our surge 81 and 260. So those would be associated with these 2 lines. So as you step through, you can see the strengthening of the surge as well as the tightening up of the rotation as we step through. So, oh, this is interesting. I had changed this. So this was supposed to be different images, but I guess we're gonna look at these. So we have our mobile mesonets plotted here, and this is our probe 1. So this is a mobile mesonet from NSSL. And it's going to make a transect of our surge here. So that's associated with our line, our blue line here. As we go through in time, you can see it's colder. And then as it's making its cross section across the boundary, it suddenly warms very rapidly. And then the mobile mesonet stops and turns around. And okay, there's the new images. Okay. So this is the same image. Again, this is probe 1. This is our line that we're looking at here. And so as we step through, okay, I apologize. As we step through, we're rapidly increasing in our temperature, and we also see our increase in wind speed and a slight wind direction shift. And then as the mobile mesonet stops and then recrosses the boundary, it gets colder again. So that tells us that our boundary is cold. Our RFD surge is colder than the embedded RFD. So my second case is June 8th, and this was an anticyclonic tornado near Goodland, Kansas. And this is the time of the tornado. So this is the time this picture was taken. The gray line is pointed to the tornado, and this is the red arrows are pointing to the rotation as well. Stepping tornado would occur. And again, must be the slightly old version of the presentation because these were supposed to be different images. But stepping through, you can see the surge event right here. And then it gets also gets colder, but it's probe one is a bit further north again, so it's not quite making a good transect. So it's kind of hard to make a thermodynamic claim from those images. So there's quite a bit of work to do going forward, but I think it's a good foundation. Basically, our TORUS data set is going to give us a unique opportunity to look at these surge events. And so far, we've seen in only 2 cases that the time scales and the spatial scales are variable, because our first surge that I showed lasted about 20 minutes, where the second one lasted about 10, but that does match what's in the literature. And it's matching spatially at about 5 kilometers, which matches some instances in the literature as well. We only have one well-analyzed case so far with the mobile mesonets making a nice transect, but that case was colder than the RFD, which is interesting because that kind of goes against our previous hypothesis. So there's more work to do on that. But any questions?
Thank you for that. There was one question in the chat. Just real quickly before we need to move on. Will TORUS be in the field for 2021? Has that been decided yet?
It has not been decided for sure yet. Awesome. I think of now.
Cool. Well, thanks for your presentation. We're going to move on to Dr. Weiss, again from Texas Tech, with another presentation on the TORUS project. So Dr. Weiss, feel free to take over the screen. And
let's see here. I tried this earlier. I guess, am I doing this right? Oh, I'm sorry. I promise I practiced this entire screen. There we go. Okay, excellent. And then click that. There we go. All right. All right, all set? Okay. All right, terrific. Thank you so much. I'm excited to talk today about the TORUS project. Ellie, my student Ellie, gave a good presentation on one facet of the TORUS project. And I'm going to give a bit more of a holistic overview of the project itself, what we're trying to accomplish, what we have accomplished so far, science objectives, etc. So the project's sponsored by the National Science Foundation, and it, like similar projects like Vortex and of course, due to the pandemic, we did not have operations this current year, so fingers crossed that we can pull this off in 2021. But you can see a list of the collaborators here, multiple universities and labs, various radar and in situ assets that were thrown at the problem. Arguably, one of the more novel platforms is the unmanned aircraft from the University of Colorado. You can actually see a view from the Tempest aircraft here near the low-level mesocyclone. And that's unique because that gives us an opportunity to sample I guess more the four-dimensional environment near these storms, and then getting a true four-dimensional depiction of the kinematic and thermodynamic gradients near these storms associated with the boundaries. And our overarching goal here is to understand these boundaries better. I think there's a lot of operational folks, on the call here, and bless your hearts, it's a tough job trying to discriminate tornadic and non-tornadic supercells. And our hypothesis is, this isn't too earth-shattering, is that there's details that are beyond our operational limitations that help us distinguish tornadic and non-tornadic storms, and part of it's related to these boundaries. That's really why we're trying to do this project and learn more about how boundaries influence near surface rotation. So as Ellie mentioned, 2019, I think everybody on the call remembers this was a big year. Just for grins, I threw together a 2-week composite of the 500 millibar height. This is a 2-week average. And you can see this huge long wave trough here in the Western US, just pretty much unprecedented. And as you'd expect in that pattern, it's just like a supercell smorgasbord, just day after day of supercell convection. So the numbers here in bold are very bloated, compared to typical years, maybe 2 or 3 times the number of cases, tornadoes, blah, 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 compared to a normal year. So lots of opportunities to have some impactful science here. Speaking of science, Ellie already spoke about rear flank internal surges. I'm going to give a brief treatment here to these next two, and then we're going to spend some more time on the streamwise vorticity currents. And that relates a lot to the data gathered with the Texas Tech KA band radars. Speaking of the radars, Ellie showed some data from these radars. A lot of people may not be familiar with our radar systems. They're like DAOs, just at a higher frequency, and I guess by virtue of including this picture, they're more intimidating. But we run at a higher frequency of 35 gigahertz. And as with all aspects of radar meteorology, it's littered with trade-offs. When we have higher frequencies, we suffer more from attenuation, especially in hail. But we also get finer depictions of atmospheric boundaries. We get finer resolution because of less diffraction of the radar beam itself. So for this type of project where we're trying to scan these boundaries close to the surface that typically lead to heavy precipitation, the radars are very well suited for this purpose. So I've shown 3 rear flank gust front cross sections here that I picked out of our catalog, if you will. And these are all different storms, different intercepts. And again, these are all across the the area south of the mesocyclone, so across the rear flank gust front. And if you look at, again, these are RHIs, so just our frame of reference, the radars in the lower left-hand side, where it's like we're taking a cheese slicer here through the across the boundary, and you can see pretty radically different depictions in terms of the density current structure. And I annotated this here just so you get your frame of reference. Again, we're looking towards the storm, so the outbounds, the red colors, the warm colors are away, and the blue colors are outflow from the storm that are coming inbound to the radar. Okay, and you see that depiction varies quite a bit. And some of the degrees of freedom that we're really trying to tackle here, partly the slope of the rear flank gust front. In sheared flow, the slope of that density current depends on the buoyancy deficit within the body of the density current itself. And since we know that tornado potential is related to that buoyancy deficit in the rear flank outflow, kind of using A to B to C logic, we believe that observables like the slope of the density currents, the head of the density current, can tell us something about tornado potential. As Ellie alluded to, internal surges. I won't go much more into that. But also things like these kind of turbulent wakes that we see in the bottom, warmer than you'd certainly expect, and sometimes warmer than the base state, which is really something. And it's quite possible, following from a theory that Curtis Riganti and Adam Houston put forward in the literature, that could have something to do with inflow air that's coming down to the surface in these turbulent wakes. So that's another thing that we're paying close attention to. Supercell. This is not my time lapse, but I wish it was. If we're looking at a supercell from the typical inflow position here, we see the forward flank precipitation here on the right. We could draw a material circuit on here, and we would, if we assumed that the environment was homogeneous, we would put that center of mass, right in the geometric center, maybe down a little bit due to the density stratification. But when we have rain-cooled air that's occurring in the forward flank, the density is increasing as we head to the right across this circuit. And we have cooler air on the right-hand side. And as a result of that, the center of mass of that circuit shifts to the right side. And just like those weighted beach balls that I'm sure we've all seen, you kind of sit those down, they roll such that the center of mass returns to the center, at least in the XY direction there. And that, of course, is vorticity. So density gradients, like we see on the edge of these precipitation regions, beget horizontal vorticity. That's obviously something we're very interested in when we're trying to understand why rotation like this is happening down low in a supercell thunderstorm. So a number of simulations have shown this. Recently, we've had some very high resolution simulations showing very intense realizations of this vorticity near the ground. And one of these is from, whoa, let's go back here. There we go. From Alex Sheath, my student, who's going to be talking, I think, two talks from now. What we see here in this simulation here, this is showing a supercell, and this area purple is streamwise vorticity, and the red loop that we see right here, this is the same red circle that we were just talking about in the video earlier. And when we look at it from the south or look at it from the east, we see that this vorticity is approaching the main updraft, and it's. I'm giving a presentation.
It's a check delivery.
Okay, thank you, sweetie.
The red mustard,
Okay.
the blue's water, and the red
Okay.
is
All right, go tell mom. Okay. I'm so sorry about that. I thought that door was locked. When we look at these simulations here, we see the streamwise vorticity going through those red material circuits. Okay, and so we see this in the high res simulations. Let's see here. The question is, do these actually exist in reality? And that's was really our charge in Taurus, was to see if we had realizations of that vorticity in the observations itself. Okay, so an example case I want to show you is from May 27th, 2019, and we see this event is the Imperial Nebraska case. Some of you may have seen the big mothership supercell pictures from 2019. This is probably our signature image from Taurus so far. And that was the end of the event. We had a number of supercells that day closer to the Front Range, including this first supercell that was closer to Fort Morgan. And you can see the same kind of structure, a little more skeletal at that point, and obviously weaker. But I wanted to contrast the depiction from the KA radars for Storm A, this weaker storm, and Storm B, just to give you an idea of how that depiction of that vorticity, that horizontal vorticity, changes. Okay, if we look at this Storm A, the Storm B, and the PPIs over here, this is a flat presentation, a horizontal presentation. You can see the hook echo regions of these supercells, and you can tell very clearly that the flow is a lot stronger. The dynamic pressure perturbations are stronger, the sucking in the inflow. But when you look at the plane of the RHI here, this is this black line right here, and we look at the depiction in the RHI over here, and I'm going to bring in, we'll count how many times the red circles appear in the presentation here. I'm again focused in on that region where the beach balls are potentially rotating, and this depiction from early on in the event for Storm A, this is a very pedestrian-looking density current, very weak outflow, and just like if you went into a fluids lab and ran a density current simulation, it would look something kind of like that. But this depiction from the Imperial period, Storm B, much more intense vorticity, much stronger realization of this vorticity, and this is in line with the streamwise vorticity current that we were looking for. If we actually compare that observation to the simulations, again, this is our simulation from Alex Sheath's work. You can see the pressure perturbation, about 2 or 3 millibars. This is a stretched horizontal tube of vorticity after all, so we expect that than what the simulation shows. But the placement in terms of altitude above ground level and in this, again, the storm relative placement are pretty much spot on. So we're pretty encouraged by that. How do I have here left? Let's see. Okay, I'm pretty much close to the end here. I do want to at least show we did have a tornado associated with this event right here. You can see the couplet in the radar data. Probably even more interesting, you can see this visual manifestation of the SVC. I didn't put the red circle in there, I should have, but we can see condensation with the upward branch of that circulation, and that gives us this nice tail cloud representation there. Again, shout out to Alex for that video. Okay, so I'm out of time to really talk about the vortex arches, so we'll let that go. But in summary, we've done quite a bit of work collecting data. We talked about the RFD surges in the previous talk. SVCs, I wanted to focus on that a little bit more because that's probably some of our more developed stuff in terms of the observations that we've picked out so far. And again, the question might come up, do we see these SVCs in all storms? And the answer is no. It's not a ubiquitous feature, and we don't see it quite as often as maybe we expected to based on the simulations. And when it does appear, it seems to appear in kind of segments, and maybe not the long continuous tail that we saw in the simulation itself, but it's very preliminary. These are very preliminary as well. So again, fingers crossed for the second field phase next year. I can't imagine it's going to match the productivity from 19, but who knows? Maybe it'll work out. So with that, I will stop, and I will be glad to take any questions anyone has.
Thanks for that, Dr. Weiss. Not too many questions for you. Just a lot of comments about the cute daughter you had there.
Oh, yes. Well, at least she had clothes on this time. She bombed the lectures earlier, so
that'll probably be me tomorrow. I'm running this show from home tomorrow, so it'll be interesting.
Have fun with that.
All right. Well, thank you for joining us. Thank you for the presentation. Looks like Jessica's joining in, and we got her in. Next up from Texas Tech University is Jessica McDonald. Her presentation is titled Properties of Thunderstorm Cold Pools Observed During the Vortex Southeast Project. So looks like you are set to go, Jessica, so feel free to start.
All right, can you hear me now? All right, awesome. So now we're switching over to a different field project. Now we're looking at Vortex Southeast. Some of this research was from my master's work that I did with Dr. Chris Weiss at Texas Tech. And then I have done additional work that I'll be presenting, and then this is motivating my PhD research. So we care about cold pools because past research has shown that baroclinity within those cold pools is important for producing the level of vorticity. So horizontal vorticity in the environment alone is not going to be sufficient because your vortex lines, as they're tilted into the vertical by the updraft, they're also lifted away from the surface, so you have nothing near the ground. However, when you have vorticity that's developed along the outflow, as shown by these vortex lines here, as those descend to the surface in the downdraft, they can be tilted into the vertical, and then once near the surface, they can be stretched by that updraft, and so then you can have strong low-level vertical vorticity. Observational studies of supercells have found that the cold pool temperature, the relative temperature, can be related to tornado production. So significantly, tornadic storms tend to have relatively warmer cold pools, as shown by the pinks and light blues in this plot here. So your warmer cold pools are going to have more buoyant air. So when you have your vertical vorticity near the surface, those air parcels will be more easily lifted by the updraft, and thus you will stretch your vorticity. However, if your air is less buoyant, it's more dense, that's going to resist your upward acceleration, so you're not going to be able to stretch your vorticity. However, this brings up the Goldilocks principle, which is that the warmer your cold pool is, that means you'll have weaker temperature gradients, and so you'll have less baroclinic vorticity generated along those gradients. So you have to find a balance between buoyancy and the production of baroclinic vorticity. So I wanted to see if these principles apply to different types of storms or environments. So during Vortex Southeast, which we did in Alabama and Tennessee, we observed a whole bunch of different types of storm modes. We had supercells, hybrid, embedded supercells, and quasi-linear convective systems. And these were occurring in a whole bunch of environments, including high shear and low cape. So this is a more of a unique data set than has been looked at in the past. Fortunately, when we looked at the cold pool deficits, we were not able to relate those to tornado production. Those results were inconclusive, but it's actually really not that surprising that that was the case. Our strongest tornado that we were able to get observations near was only an EF1, and so based on past research, you wouldn't really expect there to be a difference in temperatures with tornadoes that week. However, I wanted to take a closer look at baroclinity. So the rest of this talk will be focusing on fine-scale baroclinity, or temperature gradients, at the edges of those cold pools and how there are patterns and variability within those baroclinic regions. So during 2016 and 2017, during those springtime, we had 16 stick nets. Those are colored dark blue here. This is northern Alabama and southern Tennessee. And we call that the STESnet, or our stick net array. And we were able to expand that to 24 stick nets during 2018 and 2019, and those additional sites are colored in this light purple. And so the stick nets were able to observe temperature, relative humidity, pressure, wind speed, and direction. And from that, I was able to derive two variables, theta V and theta E. My main focus will be on theta V, that is virtual potential temperature. So that gives you an idea of your air density. And so from that, I will be determining baroclinity based on gradients. And then theta E, rotation or tornado pass within 15 kilometers of a stick net. So for this case, we defined rotation as inferred vorticity calculated from a velocity radar data that had to exceed a certain threshold. And using this, we were able to find 11 different events. However, I will only be discussing 3 of those events. The first was a supercell event from 2019, and then the last 2 were QLCS events from 2017. So diving right in, looking at the supercell case. So we had 2 supercells track across the southern part of our domain, looking at these most southern stick nets. So the first the first supercell tracks to the north across here. I have the 40 dBz outline of reflectivity, and that produced an EF0 and EF1, and then a tornado passed to this, supercell passed to the south and produced 2 tornadoes with the same ratings. What's interesting about this first supercell is we were able to get observations during a non-tornadic phase and then immediately before tornadoes. So looking at the northern observations, so this is that non-tornadic observation. So shown here is a time to space plot. So there's 30 minutes worth of data that has been projected into space, and it's centered on the time listed here. And then we have reflectivity data at 40 dBz shaded. And then we have, this is theta V perturbations plotted here, and theta E perturbations plotted here. And these are perturbations from a defined base state. And then I have it plotted here so that you can see more of the detail. So for comparison, this is the tornadic observation. You can see the tornado tracks here. And so when I was looking at these traces, so theta V is blue, theta E is green, I noticed that there appeared to be 2 different thermodynamic regions. The first one is characterized by a baroclinic zone. So you have theta V decreasing, you have gradient here, but you have positive theta E perturbations. And so this is a really nice scenario for producing baroclinic vorticity because you have your temperature gradient here, but your air could still be potentially buoyant relative to the environment. And then the second region, both of these variables decrease. So I calculated the theta V gradient across both of these regions. And so I got values in Kelvin per kilometer. And I found that for both of them, the second region had greater baroclinity than the first. But what's really interesting is that I found that the observations near the tornadoes had greater baroclinity than that non-tornadic observation. So then I did the same procedure for the southern supercell that was also tornadic. You can see the 2 tornado tracks here. And I noticed again that there was 2 regions that were present, and this one had very large theta E perturbations. And again, region 2 had greater baroclinity. And if I provide context with these values and put them all here, what's interesting is that, again, this observation near tornado is much stronger than the non-tornadic observation that I got initially. So what this means is that we're seeing stronger gradients near tornadoes. So this could mean that we have increased baroclinic vorticity production that is occurring near these tornadoes. And so that could be assisting potentially with tornadogenesis. I mean, there's lots of other factors that could be playing a role here, but this is still an interesting signal that we're seeing. I have them all plotted here, and notice the 2 tornadic observations actually look very similar to each other. And also notice that they have greater deficits than the non-tornadic observation, which is helping with producing that greater baroclinity. So then I wanted to look at my QLCS events and see if I'm seeing a similar signal. So I have to go a little bit into methods for how I'm going to calculate the theta V gradient. So linear systems are much more 2-dimensional than supercells, so that lends themselves well to repeatable methods, such as calculating a theta V gradient. However, if you have a storm that's moving across your domain, it's going to impact a whole bunch of different stick nets. But for those values of those gradients to be comparable, I have to control for storm motion and the orientation of the storm relative to stick nets. So say you have a snippet of reflectivity from your QLCS here, and it's coming up on a stick net. So the first thing I had to do is assume that my reflectivity angle, the edge of this reflectivity here, is parallel to my theta v contours. So I'm just going to assume that I can replace my reflectivity with my cold pool. So now if you imagine that this storm is moving due east, you're going to get a time series that accurately represents the baroclinity that is found at the edge of this cold pool. However, if you have a motion that's more to the northeast, then you're going to be cutting across this gradient at an angle, and so you're going to be getting a weaker gradient than what is actually present. So to fix for this, first of all, you have to calculate for storm motion so that you know what the storm motion vector is, and then you can convert your time series to being over distance. Then I found the difference of angle between the storm motion vector and the vector that goes across this gradient here. And using that angle, I was able to use this equation to basically squish my data together and increase that gradient. So now we have a much more representative gradient because we're projecting it onto the proper vector. So now that I have this data, I can look over I can look over a kilometer distance and find the theta v difference, so my gradient, and I rolled that 1 kilometer distance across the edge of this cold pool. I found the maximum value, and I'm going to take that and say that's the maximum baroclinity at the edge of that cold pool there, and now I can compare it across my entire event. So going into my first event, this is March 10th, 2017. This was a high shear low cape event. We're looking in the northeastern part of the array. So we have reflectivity data here shaded every 30 minutes. 2 tornadoes were produced in this QLCS. The first one came within 10 kilometers of, of the St. Petersburg sticknet here. And then this EF1 tornado came within 14 kilometers of the Tullahoma sticknet here. So what I ended up doing was calculating the gradient at every single one of these sticknet observations, and then I plotted them all onto the same map. So this is not a snapshot in time. This is showing both spatial and temporal changes as the QLCS is moving across the entire domain. So just keep that in mind. There is some variations across this plot, but the main takeaway here is that we are seeing that the largest theta v gradient that is observed on this map is nearest to any of the tornadoes that occur. So this is kind of similar to what we were seeing with the supercell observations. We're getting stronger gradients closer to the tornadoes. So now looking at my last case, April 30th. So this has reflectivity data plotted every hour. This case was interesting in that it had 2 different tornado-warned mesovortices. There's actually 2 mesovortices up here. The southern one produced an EF0 tornado that came within 8 kilometers of a sticknet, whereas the northern one never produced any tornadoes. So that leads to some interesting comparisons that can be made. And we also had 6 additional sticknets that we were able to set up for that day. So this plot is a lot messier than the last one that I showed. There's a lot more variability, and you can see some very fine scale stuff going on here. But the main takeaway is that these 3 sticknets here, here, and here were all associated with that southern tornadic mesovortex. And they all actually have some of the larger gradients found within the storm, and consistently so. This is over a decent amount of time. So again, we are seeing that the part of the storm that ended up producing that tornado was associated with some of the larger gradients. And the mesovortices to the north that were also tornado warned, well, they happened in a region that had some of the weakest gradients. So you are seeing quite a difference between those 2. So overall, I'm seeing those gradients near the tornadoes for both of these QLCS cases. And so that could imply that we have greater baroclinic vorticity generation occurring in this area. For that to happen, we would need favorable parcel trajectories, and unfortunately, we cannot calculate that from surface observations. So this is all just trying to interpret the data, but I can't say for sure that there was greater baroclinic vorticity generation occurring. So just to sum everything up, regardless of the storm mode, we saw this with supercells and with linear systems, we are seeing greater baroclinity in the vicinity of tornadoes or strong low-level rotation, which could imply that we have greater baroclinic vorticity generation. Past research kind of suggested that there was an opposite result since they had warmer cold pools, which would lead to weaker gradients. But those results were only looking at supercells in the Great Plains. They weren't considering linear systems or high shear low cape systems. So for my future work, I'm going to be continuing to focus on QLCS events. We are going to be trying to get some more data with Vortex Southeast, try to get more observations of tornadic QLCSs. And eventually I'll also be running some more numerical simulations looking at semi-idealized events, trying to include surface drag, Coriolis, make it as realistic as possible, to try to basically answer questions, what's causing this greater baroclinity in certain areas than others, and how is that baroclinity affecting vorticity generation? And overall, the goal is that we'll, learn more about the dynamics of these storms and how tornadoes are produced, especially in these more marginal events. And hopefully this could eventually be used to help improve prediction and warnings of these type of events. So with that, we might not have time for questions, but
I actually got
yeah.
quite a few in the chat.
Oh, okay.
So I'll ask you one here, and then if you don't mind hopping into the YouTube and answering the other two over the chat. So I'll just go with the first one. Have you considered positional effects with the strength of cold pools influencing the positioning of near-surface rotation relative to the dynamic forcing from the mesocyclone? Did you catch all that?
It's a lot of words. So if I understood it correctly, maybe that's related to how like south of mesovortices or within rear inflow jets and things like that, you could have increased gradients.
Yeah.
That could potentially affect how like the gradients that I'm observing. So we were observing multiple parts of the storm. It wasn't necessarily consistent relative to where the tornadoes were occurring. So that's part of the reason why we want to get more observations so that we can, get more consistent data sets to see how this these gradients are spatially arranged around areas of tornado production.
Cool. Yeah, there's two other questions that I think a lot of people would like the answers to. So if you don't mind hopping in and answering those in the chat. And we'll go ahead and get the next presentation started. I've been butchering names all day, but since Dr. Weiss, not Weiss, said it was Alex Sheath, I got that name right. So we have Alex Sheath, not Schuth, that's how I would have said it, with the next talk about modification of the streamwise vorticity current by cold pull magnitude. So you can go ahead and share your screen and take it away.
All right, there we go. Sorry about that. All right, so like you said, I'm talking about the modification of streamwise vorticity current by cold pull magnitude. I'm sure you guys are sick of this video in the background, but who can be sick of a beautiful supercell like this? Like Chris said, this was from the Imperial case where we got some good data in Taurus. And I wanted to kind of highlight it here because this inflow tail is really characteristic of the streamwise vorticity current. It's kind of a physical manifestation of that. We can kind of see the flow towards the updraft, and then we kind of get this solenoidal motion around it as well. So I thought I'd throw in the red circle for Chris because he didn't have it in the time lapse as well. So Chris and Jesse kind of did a good job of leading into kind of the work that I'm doing with computer simulations. So let's kind of start with the streamwise vorticity currents. So on the right-hand side, you saw this earlier. This is Lee Orff's picture of the streamwise vorticity current. There's a lot of, this is the streamwise vorticity field, and this is the forward flank here. We're looking east. And we kind of see this accumulation of streamwise vorticity along the forward flank boundary. It kind of wraps around the tornado. And in a paper that I'm working on in revisions right now, we can kind of see the maximum of streamwise vorticity located right behind the forward flank boundary. It's actually in a steady state Kelvin-Helmholtz billow that the flow is along the boundary towards the updraft and is actually stretching. And this is actually a feedback process. So the precipitation in the forward flank will evaporate and creating a shallow cold pool. It's not air from aloft falling down like it is farther to the west in the storm. And I'll talk about this in a little bit. It's cooling the inflow air. And so the convergence, as the cold pool strengthens, the convergence on the boundary will sharpen the gradient and it'll generate Kelvin-Helmholtz billows through baroclinic vorticity generation. But the flow is parallel to the boundary and it's accelerating towards the updraft. So this vorticity that's being baroclinically generated is stretched. And as that vorticity is stretched, it creates a stronger pressure perturbation, a negative pressure perturbation that further accelerates the flow, which further accelerates the vorticity, stretching it. And so it's kind of a feedback process like that. And here's kind of a diagram I had in my paper as well, where this is a vorticity budget of a parcel moving through the SVC. And the yellow line is the stretching term. And so the stretching term dominates the vorticity in the SVC. However, the green line is baroclinic term as well. And so that one is non-negligible. And you kind of need the baroclinic vorticity to start this whole process off. So some of the takeaways, I guess, is baroclinic vorticity generation is good. Horizontal acceleration is good. But the SVC only works when these two are superposed, when they're co-located to each other. And so like Jesse said, I'll kind of go by this real quickly. Baroclinic vorticity generation is a Goldilocks problem. Too warm of cold pool, not enough vorticity. Too cold, and the updraft won't actually suck that up. And the position of the boundary is really important relative to that acceleration. And so that's kind of the key point here, is that it's still unknown exactly where this horizontal acceleration, the inflow low, if you will, is situated at, if it's directly to the east of the meso or northeast or southeast. And so we might know where the boundary is, but if it's not co-located with that acceleration, then it won't have this feedback process. But we're going to focus really, in this study at least, on the cold pool boundary itself. And so the cold pool speed, generally just in a storm, is dependent on shear, cold pool strength, the deficit of the cold air behind the boundary, and the cold pool depth, the height of it. And so generally, these forward flank cold pools are around the same depth, but this cold pool strength and the shear profile around them are different. So my hypothesis, the end goal is to understand the environmental conditions that lead to the occurrence of an SVC, see if we can forecast this. If operational, you can see the sounding and say, hey, this is supportive of an SVC, I'd like to be able to kind of show that. And I also want to look at how the forward flank boundary orientation is superposed onto the inflow acceleration. So the research question for this topic is, will changing the cold pool temperature affect the strength of the SVC? There's two ways this could happen. A stronger cold pool could have a stronger gradient associated with it, and so we get more baroclinic vorticity. The other way that it could impact it is the position of the boundary itself. If it's farther south, it could be a colder cold pool, whereas a warmer cold pool might not push as far south, and so it might stay farther north and generate less baroclinic vorticity, but it could be more situated with the inflow low. So for this study, I'm working on the cold pool strength specifically. There's a couple ways to design an experiment around this. So the first one is subcloud RH. That's been shown in numerous studies, the low-level boundary layer dew points. But changing that will change the base state of the simulation. So each simulation will have a different base state, which will affect the CAPE, the LCL, LFC, etc. So we're actually changing the dynamics of the storm itself. So I don't really want to do that. Another way is looking at the aerosol concentration. There's been a couple studies that have looked at how that affects the cold pool, but that's kind of a non-linear process. It's not a direct way of getting to the cold pool. So finally, we'll end up in microphysics parameterization, which is definitely a parameterization, no means close to what reality is, but it does a decently good job. And there's multiple dials here to turn. Right now, I'm going to be looking at the evaporation rate. So this is specifically how the microphysics parameterization will interact with the thermodynamic calculation. And so if I increase the evaporation rate, it will increase the cold pool. Whereas if I decrease the evaporation rate, it'll decrease the cold pool magnitude, so it'll be a warmer cold pool. And it should have minimal effects on the dynamics of the storm. So for this study, I'm using CM1 version 19.5, 125 meter horizontal grid spacing, Morrison double moment microphysics. I used this sounding here on the right. This is the Weismann-Klemp analytical thermodynamic sounding. And the hodograph is a custom hodograph that's very supportive of supercells, shouldn't have an issue there. So I created 3 different experiments with a weaker evaporation rate of 0.9. So that should have a weaker cold pool, a warmer cold pool, if you will. The control run is evaporation rate of 1. That's just a normal simulation. And then an evaporation rate of 1.1, which will mean a colder cold pool. And these numbers are kind of important to know, as I'll be talking about them later in the analysis. All of these produced a very similar dynamic supercell. It was strong, but it was not tornadic at these times that I analyzed. It had a forward flank boundary, but there was no SVC present. And like Chris mentioned, not all storms have an SVC, and we're still trying to figure out why that is. And that's kind of one of the points of the study. Unfortunately, I didn't kind of bookend what causes the SVC or not, but that's okay, because I'm looking at the dynamics of how that cold pool interacts with the baroclinic vorticity generation, independent of the SVC. And obviously these will be interrelated, but I don't need an SVC to prove to what I'm trying to do. So looking at the forward flank, on the left-hand side, we have the theta rho perturbation shown here, and the color bar ends at -12. So you can kind of see a very cold pool on this left-hand side. This black dotted line is reflectivity, so you can kind of get your feel, hook echo down here, etc. So in this forward flank, we have this kind of broad, diffuse forward flank cold pool, but it's not super cold. And if we look at equivalent potential temperature, which kind of is a proxy for where the air originated from. If it's colder cold pool of theta E perturbation, it usually originates from higher above. But if it's kind of near base state, near 0, then it's probably not modified by descending or ascending air. It's probably kind of near the base state. So on the right-hand side, this is pretty neutral, near 0 base state. And so this air, this cold pool over here, is not affected by the descending air. And this is really what we're trying to hone in on, and specifically this boundary right here. So to define the forward flank cold pool, I centered the updraft at 0, 0. And I looked at this upper right-hand quadrant defined by this positive in the X and positive in the Y. And I looked at a volume section from 0 to 1 kilometers AGL. So this volume of air, and then I masked the air where the theta E perturbation is less than -2. So I want to get rid of that cold pool that I don't really care about right here. I really want to just focus on this. So of this slab of air, I then looked at percentiles. So the number of grid points, this theta rho perturbation or theta rho gradient or streamwise vorticity. Because if I look at an absolute maximum or minimum, that might be kind of a noisy data set. So percentiles are a little better for that. So here's a lot of information, but I'll step through it here. This is a time series of each experiment of the theta rho perturbation in that slab that I talked about. So the lighter blue is the warmer cold pool evaporation rate of 0.9, and the purple is a colder cold pool evaporation rate of 1.1. This is theta rho perturbation with time, and so we can see that the colder cold pool the larger evaporation rate was indeed correlated with a colder cold pool. And this is p-value of 4e to the -7. This is very robust statistically. I used a modified student t-test. I'm not going to go through that right now, but I have the information there if you're interested. And this is relative to the control run. If I look at the warm cold pool compared to the control run, it was also statistically significant at the 5% level of p-value of 0.04. But it's not quite as robust as a cold pool, but it still is there. So it looks like this hypothesis, this methodology, if you will, did work, where I changed the cold pool magnitude with the evaporation rate. The question is, did the gradient change? We hypothesized that a colder cold pool would have a stronger gradient. Sort of. So the results of this, the colder cold pool did indeed have a larger theta rho gradient compared to the base state, which is down here. But so did the warm cold pool. Not sure why. That's interesting. That kind of busted the hypothesis. And these were both statistically significant. They were different than the base state. So that is kind of a robust finding, but they were both stronger theta rho gradient than the control run. And if I look at streamwise vorticity, I also found that the warmer cold pool had stronger streamwise vorticity than the base state, which means that the streamwise vorticity is highly correlated with the theta rho gradient. We kind of found the same findings, that the colder cold pool was the strongest theta rho gradient, and we have the strongest streamwise vorticity, followed by the weaker warmer cold pool, followed by the control run. So that's kind of interesting. Not exactly what we expected, but a result nonetheless. So now for the second part of the project, I want to look at where this forward flank boundary is sitting at. So I identified the position of the forward flank boundary. I looked at the theta rho gradient, and I kind of objectively, subjectively found this identification line here. And I did this for each experiment at each time. And so these are these plots here. They're kind of messy, but so the evaporation rate is 0.9. Earlier times are in blue, later times are in yellow. So we can see that this boundary kind of moved north and then started moving south towards the end of the simulation for the evaporation rate of 0.9. For evaporation rate 1, similar thing, started very far south, moved north, and then came back south. And then for the evaporation rate of 1.1, it just moved north and it sat there. It didn't actually fall back south again, which was opposite of our hypothesis, go figure. So let's look at the statistics again. Right here, we're looking at the boundary angle. So of those lines, I did a linear regression, found the slope of each line, and I looked at that as the time series for each experiment. And so this is our slope on the y-axis, time in the x-axis. And none of these were statistically significant. They were practically identical, especially between the colder cold pool and the control run. If you kind of squint, you can maybe see that the colder cold pool is a bit of a higher slope and the warmer cold pool is a bit of a lower slope, but those are not robust results. So there really is no signal with the angle of the cold pool relative to the updraft. But if we look at the position, which is what we saw earlier, a larger evaporation rate is farther north, and that's what we saw. But statistically, we can show that this is farther north than the control run with a statistically significant value. A smaller evaporation rate is farther south than the control run as well. This is not quite statistically significant. It's sort of close, but not a complete robust result because of the amount of variance here towards the end of the time series. But this is an interesting result nonetheless, that our colder cold pool is farther north from our control run. And we're still kind of unsure why that is. So some of the conclusions: forward flank cold pool was changed by changing the evaporation rate. This worked, but the density gradient and the streamwise vorticity did not follow like we thought. Forward flank boundary position was not statistically significant for the orientations. Is partially significant for the north to south position, but it was opposite of our hypothesis here. And this could be tied to our acceleration area. We did not identify that. We don't know where that is. So I need to, for future work, I need to look at that. I'd like to also get an SVC environment to make sure that this is not independent of that. It's all tied together. Output at a higher temporal resolution. Each of the things I had 5-minute increments, and so that kind of affected my statistics a little bit. That kind of maybe skewed it. So I'd like a bigger sample size, if you will. Other environmental conditions like size sorting, different hodograph shapes is important to kind of capture the whole environmental conditions that support the SVC, and then finally the downstream effects that the SVC has on the supercell. If you identify an SVC in the real world, operationally, can you know what effect is it going to have? Is it going to have an effect on a tornado or is non-tornado? So anyway, with that, I will take any questions.
Thanks, Alex. Again, very interesting presentation from you guys over at Texas Tech. Don't think we had any questions come across, so we'll go ahead and leave it at that. And again, thanks for joining us, and thanks for your presentation.
Absolutely.
I think you might have had one question in the chat, so if you want to go in there, we'll go ahead and let Janik take over, if that's okay.
Yep, no problem.
All right, hi Janik. Next, we have one last presentation in this session. Insights into tornadogenesis from idealized simulations. So Janik, if you want to go ahead and share your screen, we'll go ahead and get started.
All right, thank you. So, hi, I'm Yannick. I'd like to wrap up this session by talking about my PhD research and what idealized simulations can teach us about tornadogenesis. So as probably all of you know, supercells are characterized by rotating updraft and produce the strongest tornadoes. And in order to produce a tornado, most generally we need two things to happen. First of all, we need intensification of the low-level updraft, and supercells are ideal for this because they have this rotation, and by ingestion of the low-level shear, they can induce dynamic lift and really increase the low-level updraft, as we already see in this picture here from a supercell in New Mexico last year. And as we saw in the presentation before, the SVC might play a role in this as well. The second thing we need is of course vertical vorticity near the ground that can be intensified by the stretching of the updraft. And it has been generally accepted that this vertical vorticity is produced in the cold pool, then brought to the surface by a downdraft and tilted into the vertical as well. So we have these two main processes that are included into the tornadogenesis process. But what we wanted to find out is one of them more important than the other. For example, some recent studies have suggested that there's always enough vertical vorticity in the cold pool, but that it's really a matter of the low-level updraft to intensify and stretch this given vorticity effectively to create a tornado. The difficulties that we have when we want to find out the relative importance of the updraft compared to the cold pool are that they're not easy to observe, as probably all of you know. And even modeling studies have their problems because we can't design controlled experiments on the low-level updraft and the cold pool because they both depend on the dynamics of the storm. So what we did is we used an approach by Markowski and Richards in 2014, an idealized simulation approach. They used a cylindrical heat source, which I represented as a red cylinder here, to produce warming in their model and therefore an updraft that simulated the updraft of the supercell. And they used a heat sink, which is this blue cylinder here, to produce cooling and produce the cold pool. And with this simple setup, they were able to reproduce the structure of a supercell pretty well and even tornadogenesis. Now, one of their findings was that you really need the strong low-level shear to dynamically increase the low-level updraft, which I represented by this gray sketch here. So what we did, we adapted this approach and directly simulate this low-level updraft by a shallower heat source to directly do controlled experiments on it. And we also used an array of time-dependent heat sinks instead of one constant heat sink to produce a more realistic and heterogeneous cold pool structure. I'm not going to go into detail with the CM1 with the model setup, but I basically used the CM1 model with a simple base state. So let's jump right into some examples and how these simulations look like. On the left, you can see the potential temperature perturbation near the ground, and we can see that this array of heat sinks produced starts here a heterogeneous time-dependent cold pool, as we would also see in real storms. And the effect of that is that when we look at the vertical vorticity on the right, that the vertical vorticity is produced on the cold pool, as we would expect. And then these patches of vertical vorticity move into the updraft area or below the updraft, which is outlined by the. So with this setup, we were able to directly control the updraft strength by changing the magnitude of the heat source and control the cold pool strength by changing the magnitude of these heat sinks. And then we were able to do controlled experiments, changing one of them separately from the other. What effect does that have? Let's look at two examples. On the left, we have a simulation with a weaker heat source, so weaker low-level updraft. On the right, we have a simulation with a stronger heat source. And when we look at the beginning of the simulations, they should restart soon. They look really similar because like I said, we have the cold pool. The cold pools are both the same in the simulations. So we have these vertical vorticity maxima that move into the updraft. But only in the right case, with a slightly stronger updraft, we finally get the intensification to a tornado-like vortex with tornadic wind speeds. Well, in the right case, we get intensified low-level rotation, but the vorticity maxima move out of the updraft again before they can form a closed vortex on the tornado. So now that you've seen some examples, I'd like to summarize all the basic results from this study in this simple plot, which represents 88 simulations, like the ones you saw before. And each pixel in this plot represents one of the simulations you saw with a combination of a heat source strength on the x-axis and the heat sink strength on the y-axis. So the further we go right on this plot, we have simulations with a stronger low-level updraft, and the further we go to the top, we have simulations with a stronger cold pool. And the color you see is the average vertical vorticity maximum in 1 kilometer above ground level. So basically the average vortex strength in this simulation if there was a tornadic vortex. And in all these white or light cases here, there wasn't any vortex forming, so the average vorticity is really low. And in the cases where we get into the more brown colors and the darker colors, the vorticity was pretty strong. So I want to show three really interesting things here. First of all, we see that both the updraft strength and the cold pool independently changed the results of the simulations and determined tornado potential. So for example, in these simulations down in the right corner, we had a really strong updraft in the simulations, but the cold pool was pretty weak. So there wasn't enough initial vertical vorticity, so it couldn't get intensified to tornado strength. The second result we see is that in some cases, small changes led to tornado genesis success or failure. So in the reason, we called this a bifurcation region, which is this region down here, like the middle of the plot. And in this bifurcation region, we see that what small changes in the updraft or the cold pool could lead to the production of tornadoes in the simulations. And unfortunately, the implication that this has for forecasting is that for storms in this bifurcation region, accurately nowcasting or forecasting which storm will produce a tornado is almost impossible because these storms will almost look identical in the observations we can get. A third result that we found is what Alex and Jesse already talked about, is that there's a range of cold pool temperatures that is optimal for tornado genesis, which is called the Goldilocks zone. So if the cold pool got too cold, then the buoyancy was too negative to sufficiently provide for vorticity-rich air for the tornado, and the vortices tended to be weaker and short-lived. One final result that I wanted to show is when we look at the time it took for tornado genesis in these simulations. So this plot shows the same simulations as the left one, but this time the time it took for the first tornado to form. And when we look at these greenish or yellow cases, it took over 100 minutes for the artificial supercells to form a tornado, while in the blue cases up here, it only took like 5 minutes. So we see that the low-level updraft strength and the cold pool combined have a huge effect on the time it takes for the first tornado to form, which also might have really important implications for forecasting. And if you're interested in the details of the study, it's going to be available in the Journal of Atmospheric Sciences early on and released in a couple of weeks. In the final 1 or 2 minutes that I have left, I'd quickly like to talk about what I'm working on right now, because we really wanted to find out why these small changes in updraft and cold pool strength could lead to tornado genesis. And the hypothesis that we have is that there's some kind of instability or feedback loop going on, that the initial vortex has to reach a certain strength, and when it can, and then it can self-sustain itself by ingesting vorticity again and again. And the way we want to look at this is, again, by idealized simulations, producing an artificial updraft, again outlined by this black line here. And then this time not using a cold pool to produce the near-ground vertical vorticity, because cold pools make, as you saw in the presentation before, make things really complicated. But producing an artificial vorticity source, in this case an elliptical shape, which then intensifies below the low-level updraft to a vortex, and we want to look at how this intensification process is happening. This showing some first results that we found. So we looked at, like I said, we looked at different stages of the vortex, and if we look at posits on the left side that move into the vorticity maximum at early stages of tornado genesis, we see really different mechanisms than when we look at later stages when the vortex is already formed. And don't be confused by these line plots down here. That's basically showing the vertical vorticity budgets. But also, again, like I said, we see that the posits at early stages of tornado genesis show really different process of vorticity intensification than the later posits. And we're hopeful that this is going to give us some more insights about tornado genesis, because this hasn't been looked at a lot this far. And with that, I thank you for your attention and be ready to answer any questions.
I had one question. You said there's really not a good way of seeing the cold pool strength in real time when looking at a thunderstorm.
Yeah, I mean, cold pool strength, like, as we saw in the presentations before, there's not really one value that defines the cold pool strength. For example, Ellie talked about the role of internal surges, which can have a completely different temperature than the rest of the cold pool, and we don't really know what part of the cold pool actually has the importance in the tornadogenesis process so far.
Okay, and then one last question is, how do you think storm motion and speed of a supercell interacting a cold pool would affect the simulations?
So in these simulations, the speed was basically fixed because we fixed the updraft and the cold pool relative to each other in the center of the domain of the simulation. So I can't really say much about that. We wanted to exclude these factors to only look at the effects of the cold pool strength compared to the updraft strength, and exclude external tornadogenesis failure mechanisms such as surging outflow or something like that. So from these simulations, I don't want to comment on that.
Okay, sounds good. Well, that's the only questions. Thanks for that. Thanks for your presentation. That'll do it for us for this session 3. We're going to take a 30-minute break or so we'll be back at 2:45 with our first keynote speaker of the conference as we begin our water portion of today's conference. So we'll meet back here at this current stream. We'll keep everything up, and we'll be back in about 30 minutes or so at 2:45. Got about 5 minutes left until we start our last session of the day. 5 minutes left. All right, it's 2:45. We're just waiting on our speaker to arrive, and then we'll get started. Just sent him an email, so hopefully he'll join us soon. All right, welcome Dr. Gutzler to our conference. We'll go ahead and start the session for the afternoon session for water. Dr. Gutzler is from the University of New Mexico, and he is our first keynote speaker for this conference. And Dr. Gutzler, we just wanted to show you that for our thanks and appreciation for this conference, we will be sending you in the mail a plaque of in recognition of your keynote presentation for our conference. Normally we like to give these out in person, but that's not going to happen this year. So we'll hopefully get those out in the mail tomorrow. So we thank you for taking the time to be one of our keynote speakers. And if you want to go ahead and start the process of sharing your screen, we'll go ahead and get you started.
All right. That didn't look much like the state of New Mexico, Nick.
Well, that's true. We're expanding our horizons a little bit this year.
No, I
and,
appreciate the opportunity to be with you. Is that working? You don't see it yet. Okay, let's see if I thought I did that. Let me try it again. Oh, that's what I missed. There we go. Great. Thanks, everyone. And it really is a pleasure to be able to share some of our research with you. We're going to extended range prediction, namely the seasonal prediction of stream flow. We'll be talking about the Rio Grande as seen in that plot to the lower left. The talk is about how we make seasonal predictions of stream flow, looking at the Rio Grande headwaters. And the major point I want to make is that this sort of hydrologic prediction is being developed and is at a really exciting stage of research in terms of improving predictions. And I think a lot of the expertise that meteorologists have developed over the decades is going to be really valuable as we think about the predictability of this system from a hydrologic perspective. And I would like to put in a plug for integrating this sort of hydrologic prediction with the kinds of operational seasonal outlooks that NOAA already creates and disseminates for temperature and precipitation. So the basic boundary conditions here are that the Rio Grande, which flows out of Colorado through New Mexico to the south, and then forms the international border between Texas and Mexico, is the major river in this part of the world. I'm sitting right here in the middle of New Mexico and Albuquerque. The water almost all comes from snowpack up here in southern Colorado, and we will be focusing our attention on a stream gauge that folks in Colorado call Del Norte. I don't think too many people in Colorado speak Spanish, but we'll talk about the Del Norte gauge. And we are asking how we can make seasonal predictions of stream flow past Del Norte. We're going to be way up here because Del Norte, as we'll see in a minute, is located right where the river leaves the high peaks and flows out into a big farming valley called the San Luis Valley. And once we get beyond Del Norte, it's difficult to interpret gauged flows in terms of climate variability because the effects of human management in diverting water out of the river and doing so interannually varying way make interpretation of the stream gauge data difficult. To make things harder, the climate is changing in such a way that our ability to make these seasonal forecasts is diminishing. We know, and we'll show you in a minute, that the temperature is increasing rapidly throughout the Mountain West. Snowpack, not surprisingly, is diminishing. And so the major source of both water and predictability of flow is changing, which is changing the basic ground rules for making water supply forecasts, and that is the topic of our research. Okay, to show you how we can make seasonal forecasts of stream flow for a snow-fed river, I like to show this plot on the left. I'm cheating a little bit because, in fact, this doesn't refer to the Rio Grande headwaters itself, but to the next basin over. But the other reason I want to show this is because it was generated more than a decade ago by the next speaker, Kerry Jones, when he was doing a project at UNM for his master's degree. And it shows the seasonal cycle of snowpack at the top of the headwaters of the San Juan River. But the basic idea is this black line on both of these plots is the average seasonal cycle of snow accumulation and snow melt. And so the snow in the Southern Rockies increases over the course of the winter and early spring. On an average basis, reaches its peak snow at right around the beginning of April, and then we have a rapid melt season after that into June on average. And that is the major supply of water to the river. And the reason we know that, is that if we look at what we call the annual hydrograph of stream flow at the Del Norte gauge, we see a very clear snowmelt runoff season ramping up in April as the snow starts to melt and peaking in May, June, and July. So we have a stream, a river that's largely fed by snowmelt runoff. But more than that, what Kerry has done is on this left plot shown the individual hydrographs, those are the light lines, for all the years in this record where the snowpack on April 1st was below the black line, below average. And over here on the right are all the years in the data record where the snowpack on average was above the black line on April 1st. And what you can see is that to a pretty, for most years, the deficient snowpack years were deficient for much of the snow accumulation season. And for most all of the years with above average snowpack at the time of peak snow, the snowpack was above average for months leading up to that date. So we actually get predictability of stream flow based just on observing the snowpack, not just at the time of peak snow, but often earlier in the year as well. And for many decades, we've been able to make statistical forecasts of the total water supply coming down the river, which water managers downstream are keen to receive, based just on observing the snowpack in the mountains in the headwaters region. So we get forecasts that look like this. This is the operational outlook that's carried out by the Natural Resources Conservation Service. The colored dots represent an estimate of above or below average flow. There's where Del Norte is. We're looking at the Rio Grande headwaters in southern Colorado. The Rio Grande flows out of the headwaters up here, passes Del Norte, and last year, this is a year-old slide, the projected seasonal runoff past Del Norte was nearly 150% of the median long-term average. But there's a problem, which is that water managers in Colorado and New Mexico and West Texas have perceived that this outlook is getting worse with time, which is not supposed to be happening as we learn more about hydrology and climate, that the forecast has been losing predictive skill. In addition to that challenge, that gives us an opportunity, I think, to start to move beyond the sort of regression-based forecasts that we will assess in this talk and to start to move this hydrologic outlook toward a kind of operational forecast that with which we've achieved some success in the climate business. And I will end the talk here in a few slides talking about the opportunity we have to develop this. So here's the problem. Over the course of time, since the late 1950s, this green line represents the first April snowpack, averaged over those yellow dots on the left, the snow course sites in the Rio Grande headwaters. And we've included a few more that are actually not feeding into Del Norte just to try to get a better statistical average. And what we see is a lot of ups and downs from year to year, and an overall trend headed downward. And if we squint at the numbers, that trend is really significant. And it represents roughly a 25% decrease in the average snowpack, just estimated from that straight line fit to the data over the past half century, which is a very big deal for water in the Southwest. And that kind of trace, I can tell you, is not atypical compared to other headwaters basins in the Mountain West, for reasons that we'll see, I think, on the next slide that have to do with the temperature warming up a lot. Here is the annual streamflow trace at Del Norte. It has a very minimal decrease in the overall total annual flow. But if we look at the difference between the first and second halves of the record that's hidden in these annual numbers, that's the bars here starting at the beginning of the water year in October through September. These represent changes on a month-by-month basis in this stream flow. And what we see is a decrease in flow in the later months of the runoff season in May, June, and July, and especially June and July, and an increase in flow earlier in March and April. So in other words, even if the stream flow isn't decreasing overall yet, the runoff hydrograph is shifting toward earlier dates. And that's consistent with what we would expect in a warming climate, earlier snow melt. And here's the basic reason for earlier melt and less snow, and that is the temperature is going up a lot in southern Colorado and throughout the Mountain West. Just an average of 3 Fahrenheit or so increase in recent decades. Even at a time when the precipitation is not declining. And if anything, there's a weak increase here in precip. And so we notice that the snowpack in the Rio Grande headwaters has been decreasing sharply despite a weak increase in precipitation. And that increase is largely concentrated in the winter and early spring months. So we're getting less snow even while there's a little bit of an increase in winter precipitation. So in terms of predictability, I'll summarize an entire paper's worth of assessment of how we might predict stream flow based on climate variables with one slide. And it's a complicated slide, and it's shown here. So what we're looking at here are a set of bars that each represent a 30-year average. And this each bar with the little snowflakes represents the fraction of the interannual variability of stream flow during the runoff season at Del Norte that's accounted for by 1st April snowpack and nothing else. And so back in the halcyon days of hydrologic forecasting from 1951 to 1980, this R squared value is about 0.8. In other words, we could capture 80% of the interannual variability of stream flow over the entire runoff season with one number, and that's just how much snow there is in the Rio Grande headwaters on April 1st. That's a very fine predictability score for a seasonal forecast. But as the decades go on, that R-squared value in running 30-year periods goes down to the point where by the 30-year period ending in 2015, that R-squared value is declined to less than half. And there is a direct relationship between the predictability of runoff accounted for by snowpack, and it's going down. And if that is our major predictor, then we're in trouble. So if we just ask where's all the streamflow variance that's now unaccounted for by snowpack, can we attribute it to anything? We look at these other bars. There's a little bit associated with temperature. Those are the brown bars here. And much more of it is associated with these green bars, and that is the annual value of springtime precipitation after April 1st. So in other words, as the snow melts and we have less predictive skill from just 1st April snowpack, more and more of the variance of stream flow is accounted for by the precipitation that falls during the snow melt season itself. And that's trouble for predictability because remember, we're simply observing 1st April snowpack, whereas in order to capture this variance associated with the green bars, we would have to make a prediction of springtime precipitation. So those results are summarized here in these pie charts. The part of the pie for the first half of the record and the last half of the record, we have 100%, that's the whole pie, and the fraction of variability of runoff season stream flow accounted for by snowpack is the snowy part of the pie, and it's going from way more than half to less than half. More of this variance unaccounted for by snowpack is being accounted for by spring precipitation, but the wedge associated with just residual variance of stream flow unaccounted for by any of these three variables is going up. So we have reduced predictability according to this regression-based analysis, but an increasing component of variability associated with precipitation. And it's mostly precipitation, not springtime temperature, which are these two columns here. Our best bet, according to this analysis, of precipitation that's falling after peak snow. And so what can we do to use those results and actually try to build a better forecast product for predicting snowmelt runoff beyond just using snowpack? And one is to improve those estimates of snowpack. So that is still the most important predictor of snowmelt runoff in the Rio Grande headwaters. But we have sort of 20th century style techniques for estimating snowpack. As I showed you, the estimates that we used were based on a handful of in situ snow course sites. There are more SNOWTEL sites up in the headwaters, but they're still point-wise measurements. And there's an active effort going on to try to come up with a spatially integrated volumetric estimate of snowpack in the headwaters using a combination of remote sensing techniques. And that has to be the future. The overall snowpack melts and the snow line rises, then it will be harder to use in situ measurements that are fixed to measure interannual variability of snowpack and remove the interannual variability from a long-term trend. The analogy I want to draw here is the shift from using point-wise weather measurements based on surface weather observations and radiuson stations to a system where we use those point-wise measurements and assimilate them using the forecast model itself to create better initial conditions for weather forecast models. This is the same process We're now just going through the same process here on a hydrologic system a half century later. And a lot of the lessons that meteorologists have learned to develop assimilation systems to translate pointwise measurements into more robust, spatially integrated measurements is the way forward in terms of improving the initial conditions required to make these forecasts. Another reason to move toward an assimilation system is that the way forward here at some point will be to convert the regression-based statistical forecasts into a more dynamical forecast using a coupled climate hydrologic model. NOAA is starting to do that at the West Gulf River Forecast Center. But in order to make those forecasts better, we need to improve the initial conditions for the forecast, which is the snowpack itself. Secondly, none of the current hydrologic forecast systems incorporate climate forecasts, but our analysis suggests that in order to move forward, we're going to have to use an actual forecast of spring precipitation, which gives us yet more motivation to improve those seasonal outlooks of precipitation and then incorporate them into hydrologic models. So my own vision of the future is that the hydrologic forecasts and the climate forecasts get integrated. That's going to be a big effort, but it's got to be the way to move forward. Here is the current seasonal outlook for next winter. The later spring outlook doesn't have much skill, but this one does, because we are headed into a La Nina winter. As many of you know, these forecasts are interesting in and of themselves, and certainly in around Albuquerque, we pay a lot of attention to them. Happily, we live in a part of the country where there is considerable seasonal predictive skill for temperature and precipitation, especially associated with the ENSO cycle. And this is largely a La Nina-based forecast. And the way we know it's a La Nina-based forecast is we can compare it with the same forecast for the winter season that NOAA generated 22 years ago before, as we moved into yet another La Nina winter. And while there are important details that are different between these two winter outlooks, 22 years apart, to a pretty good first approximation in our part of the world, they look awfully similar. And that's because it's largely just based on the historical response of temperature and precipitation to La Nina, increasingly as expressed by dynamical forecast models tuned to do seasonal climate forecasts. So integrating this kind of climate information with our hydrologic outlooks has got to be the way forward. Okay, so I'm just going to wrap up and say that water supply outlooks are right now, in my view, at kind of the same place that weather forecasts were at way back in the 60s when dynamical forecasts were introduced and were starting to improve. Old people like me and Nielsen Gammon remember the days when we were young pups, right about the time when dynamical weather forecasting was totally supplanting the best efforts of genius level old-time forecasters like Dick Reed and Fred Sanders. But that's a really exciting time to be part of the forecast development effort. So getting these forecasts of water supply done better is important. The public cares about them, and I think we have a path forward to make them better. In particular, these are going to be more important for water supply in places that are chronically short of water, and we happen to live in one of those places in New Mexico and certainly West Texas anyway. There are no definitive long-term trends yet in stream flow, but they are projected to occur as the temperature continues to rise and the snowpack goes down. There's another application of our research to long-term projections of stream flow, but that's a different talk. The first order effect of diminished snowpack is to decrease the seasonal prediction skill. We see that even before we see overall decreases in stream flow. And precipitation in the snowmelt season, the snow ablation season, is becoming more important as the snowpack melts. And we think, based on our work, that snowpack and spring precipitation are the two climate predictor variables of most importance for the outlooks, at least in the Rio Grande Valley. We'd like to look elsewhere and see to what extent that conclusion is true for other important snow-fed basins like the Colorado. But all of this is, I think, represents a pretty logical extension of what we've been doing on the weather and climate side in terms of improving our ability to make really socially relevant outlooks on the seasonal timescale. So with that, thanks for your attention. I hope I've piqued a little bit of interest, and if folks have any questions, I'd be more than happy to try to address them. Thanks again to Nick and John for arranging for me to give this talk. It's my pleasure. Thanks.
Thank you, Dave. That was a great presentation. We had one question from Dr. Nielsen Gammon, and he was wondering how much cross-pollination is there with streamflow predictions in the Colorado River Basin and the Sierra Nevada?
Do you mean in terms of the actual stream flow itself, or the way the predictions are done?
Let me see if he clarifies. The methods.
The methods, from the NRCS perspective, the methods are essentially identical. So they have so they use a regression-based forecast, and that, from the NRCS perspective, is the way they do it. Of course, the terms in their regressions that include other variables like the antecedent stream flow itself and so forth, those predictor variables are tuned not just to the basins, but to each prediction point. But the general philosophy of how one makes the outlooks is pretty standardized across the West.
Okay, great. Again, thanks for joining us. Thanks for agreeing to be one of our keynote speakers. I think a lot of people found this presentation very interesting and kind of a thing we don't think about too much in Texas, but has a large impact as that water comes downstream. So with that, we'll transition to our next presentation, which you kind of alluded to with Carrie Jones. I didn't know y'all had that connection before we put Carrie right after you, so but we'll take it.
Hello, Nick. Good afternoon. How's the audio? Okay. See if I can do this without messing it up. It's always humbling experience to follow my good friend and mentor, Mr. Dave Gutzler. So Nick, I'll wait for a couple cues if you're seeing the screen and the audio. Okay, hang on. That's never a good sign. You would think after 6 months we'd be experts at this, right? So. Okay, well, good afternoon, everyone. My name is Carrie Jones here at the Weather Service in Albuquerque, and as I said, it's always humbling to follow Dave Gutzler, but we're going to switch gears a little bit and talk about burn scar flash floods, and that's kind of a topic that's near and dear to my heart, in addition to stream flow and snowpack, I should add. And I've been thinking, what's the connection between, here we are kind of in the New Mexico section of our talk today, but kind of what's the connection between kind of my topic and Texas? And this is a photo I took back in 2018 This is the Ute Park burn scar. That's US Highway 64. And there's a lot of goodwill and a lot of tourist money that flows along that stretch of highway for family and friends in Texas and Oklahoma that are getting going westbound, I should say, into the mountains of northern New Mexico. And so I want to talk about, at least here locally, kind of what we've done in terms of decision support, but more importantly, kind of how it's evolved. And I again try to make some connections again with our good friends and neighbors in Texas. So burn scar impacts are certainly Mexico. We've Colorado, much of the western U.S., and even our friends on the East Coast and the Appalachian region. But one challenge that we do have with burn scar is that burn scar impacts are often extend beyond the first year. And this photo here, my friend Barbara Judy, who was with the Park Service at the time, this was a flash flood back in July of 2013, actually during the early morning hours, just after midnight. And there was a wall of water that was 15 to 20 feet deep, moving through Upper Frijoles Canyon, Bandelier National Monument. And in fact, the park staff received calls from backcountry campers indicating kind of a loud roaring sound during the night. And as it turns out, this was a flash flood that was obviously significant. You can see the stretch marks from the woody debris that was in the floodwaters at the time. But I think more importantly, this flood occurred 2 years after the fire. And therein lies one of the challenges with burn scars. And in fact, the fire that's kind of in question here is the Los Conchas fire. And that was back in 2011. And in fact, the 2011 and 2012 fire seasons in New Mexico were really unprecedented. The Los Conchas fire, which you see here, this is a GOES visible image, in 2011 scorched about 150,000 acres of really pristine areas up in north central New Mexico. It was the largest wildfire at the time. And then naturally the following year, 2012, an even larger complex down in southwestern New Mexico burned nearly 300,000 acres. So that's close to, if I do the math, I think that's over 400 square miles. And so that still stands as the largest fire in the state's history. So really our early efforts to develop decision support tools for burn scar flash flooding, they certainly evolved since 2011, but we still have some challenges that I'd like to kind of talk about here in the next few minutes. And I guess just for our meteorologists that are on the call, even for New Mexico standards, June of 2011 was kind of off the charts. The day the Los Conchas wildfire erupted was a day where we were mixing up to 450 millibars. So that's about 20,000 feet AGL, give or take. Of course, very dry, very hot, just after the summer solstice. And the image to the right that you see there is actually our former IMET, Brent Wachter, captured the image of the smoke plume of Las Conchas as it was chewing through about an acre a second. So about 60 acres a minute, roughly over like almost 45,000 acres in a burn period. So tremendous, extremely critical. So we do really well, generally speaking, at predicting these very critical extreme fire days, as we've heard earlier in the conference. This was also a day in late June in New Mexico where we had winds of 35 to 40 knots at the top of the mixed layer, which is really unheard of in June in New Mexico. And unfortunately, it was a down power line. A tree took down a power pole, and that's what sparked this fire. And as I said, at the time, it was the largest in the state's history. The other challenge with burn scar flooding is the rapid onset. And so the image on the left was captured by an emergency manager just a few days actually before that fire was 100% contained. So it took about 40 days to contain it. So it was officially declared contained on August 3rd of 2011. A little over 2 weeks later, we were having our first really devastating flash flood. Now, we had a couple of flash flood events prior. In fact, actually, when the fire was active, we were putting out flash flood warnings. But the real devastating impacts did occur just a short time after the fire was contained. So again, that's a challenge, as you can imagine. I mean, trying to ramp up and scale decision support efforts, kind of going from fire mode to flood mode, is just something that we deal with in New Mexico. And we've certainly seen it on a number of occasions, but I think this case was really a great example. And I do have a little bit of a personal connection to this particular time period. So I experienced my first ever burn scar flash flood in real time, start to finish, August 22nd of 2011. And I was up in this area doing some flash flood survey damage, surveying flash flood damage from a almost equally as big flood that occurred the day before. So the image on the left is actually kind of a screen capture. I was going to, in real time provide you some video, but I'll kind of spare you the gory parts of video through virtual presentations. But we had a very significant flash flood on the 21st. And then I happened to be up in that area on the 22nd. And like any good, dedicated NWS employee, I called the office and reported what I was seeing in real time. So that's yours truly there in the video capture. But this is the first time in my career that I've actually witnessed kind of a flash flood in progress. And it literally sounded like a jet engine coming down the canyon. Unfortunately, the apple orchard that you see kind of pictured there was in the Dixon family for generations. It wiped them out. In fact, they pretty much sold all their equipment and moved after this event. So very devastating, very high impact. But it really was this event back in 2011 that really kind of sparked my interest in trying to better understand not only the science of burn scar floods, but what we can do as an agency within Weather Service to really have an impact, in terms of public notification and warning and so forth. So as we kind of went through after 2011, of course, 2012 was an equally as bad fire season. But our early efforts in terms of DSS were really focused on maybe 3 or 4 things. We literally, the burn scar thunderstorm threat matrix that we still use to this very day was developed by forecasters on a midnight shift. And I'll give a shout out to Daniel Porter, our science operations officer, who at the time was the individual on that midnight shift that literally brought up PowerPoint and said, we've got to figure out a way to communicate the threat. And naturally, you kind of, the green, yellow, red is what we came up with in 2011. And actually, that was one day after the first burn scar flood warning that we had issued since probably 2003. So that threat matrix is now fully automated. It falls out of our grids. But at the time in 2011, it was literally the creativity of our midnight shift. We were leveraging Twitter as well in 2011. I guess we may or may not have had an unofficial Twitter account at the time. Most NWS Twitter accounts didn't come online until February of 2012, as I recall. But we had kind of worked up our ITO a version of kind of a situational awareness with Twitter on our intranet page. So we could still see, it wasn't two-way like it is now, but we could still see what was coming in, which was helpful. We value added our warnings, not unlike we do today with like low water crossings, mileposts, that sort of thing. And then we also began kind of our weekly weather webinars, our weekly engagement with media core partners that actually started in fall of 2009. So we had almost 2 years under our belt to kind of develop those relationships that are so critical when it comes to these. So our GIS talent in the office to kind of, the image on the left there, you can see the thick red line is the outline of Los Conchas. It's a big burn scar, and so in 2011, we were pretty much, anytime a thunderstorm crossed the burn scar, we were pumping out a flash flood warning or a flood advisory. But by the time we got to 2012 and 2013, we said, hey, we've got better information. We know where high intensity burn areas are located within the perimeter. And so we customized call to action statements within WarnGen. We also connected with BEAR teams. That's the Burn Area Emergency Response teams that come in after wildfires and assess mostly kind of a hydrologic assessment. And we connected with our partner agencies. I work closely with Ann Tillery, who's with USGS. Ann is an expert in debris flows and modeling debris flows. And we took this opportunity to really kind of dig into the science. And that was kind of what we were doing through that period. And then also installing a lot of real-time precip gauges. That was also a piece of it. And then came 2018 and the Ute Park wildfire that I described earlier. This was kind of in my career, this was the first burn scar to significantly impact a major U.S. highway. And that U.S. highway was U.S. Highway 64. It's also located in one of the poorest radar sampled regions of our CWA. And so I have there on the graph, that's the 230 kilometer range ring. So it's about, about 142 miles, I think. So really for Albuquerque, Pueblo, and the Cannon Air Force Base radar, we're on the edge. In fact, we're just beyond the edge at Cannon. So we're on the edge of the radar. There is no mobile coverage in this particular part of the state, which is not necessarily unusual, but it's certainly a challenge. And then the other thing I'd point out is that, the Ute Park wildfire is not the only burn scar that we were kind of monitoring. It was certainly the largest, but it wasn't the only one. We've had about 2 dozen wildfires since 2010, about a dozen since 2015 that are pretty active. So I'll finish with kind of how things have evolved in the last couple of years. It's real-time DSS. I think Rick earlier this morning mentioned, his first smartphone, iPhone, for him was like 2009, 2010, pretty similar for me. We integrated our first smartphone into operations in June of 2015. Now, this is certainly not novel, right? Plenty of offices had been using text messaging. In fact, there was an AWIPS application years ago that you could send SMS text, but it was much harder to actually get video and photos and that sort of thing. So that really did, starting really in 2018 with this burn scar, we started to ramp up our efforts with our text messaging. So we had folks like state police, DOT, emergency managers, our state EOC. You can see there we had up to 12 people on one group message. And it was kind of this continuous communication throughout generally our monsoon season, right? Short duration, high intensity rainfall. We also kind of, I know Patricia did a great job highlighting the power of those tools, and we certainly have leveraged that in our office. But again, having that iPhone in operations kind of active and utilized has been a tremendous game changer for burn scar coordination. So on my last couple of slides, I'll finish with, when rubber meets road, or when rubber met road, in this case, I can say, in my career, it'll be going on 29 years next February. It's the first time that I can recall, and most of my career has been in Albuquerque, but it's the first time that I can recall that, in this case, a U.S. highway, all right, a pretty heavily traveled stretch of highway, was closed based on a short-term forecast of essentially garden variety thunderstorms. We're not talking about anything really that significant. Certainly, pretty ordinary. It's an ordinary thunderstorm in an extraordinary environment. And of course, this is all through text communication. So I just happened to be I believe, this was 2018. And we were texting. So I wasn't really part of the conversation. Our office was communicating with the decision makers, saying, hey, we're looking at some pretty good storms maybe coming in. This was a northwest flow case, as I recall. So there was a good storm near Angel Fire, New Mexico at the time. But it was actually the storm that looks a little innocuous on the edge of the radar, effective radar range, that was of concern. And the X kind of represents where the burn scar was. So they were shutting down the road, not once in this case, but I think they actually shut it down 15 times in the course of 2018 and then 2019. Of course, we had a very poor monsoon season this year, so we didn't have as many incidents. But I'm proud to say that there's been no impacts. So all our good friends from Texas, Oklahoma, Kansas that are coming, westbound with fifth wheels and RVs, that may have been totally clueless, how serious a threat it was. I think this literally, I think certainly saved some, well, we'll just say saved a few phone calls. How's that? And so I think my last slide to summarize is that pre-existing relationships, building trust does take time, as we all know. It's the nearly continuous communication flow during these critical times. Now, I mentioned earlier multi-year, multi-season, so we're mostly focused in the monsoon season for these type of events, but we can certainly get them anytime. Engaging with our partner agencies and experts. There are debris flow experts within GS that's in terms of modeling, and that's what they do, and trying to connect that piece. It shouldn't necessarily fall to any WFO to try to figure this stuff out. So that was really key. I would think that DSS as part of service backup needs to be part of the discussion. El Paso is our primary backup office, and El Paso deals with is important. And then lastly, weather forecasting is a humbling profession, as we all know. And I would add that burn scar flash flooding is especially humbling. And we certainly had our misses. I mentioned the text string. We would have an EM that would show us a video of a pretty serious flash flood, and we missed it. That does happen. So I will end with that. And I know we're a little bit pressed on time, but I'm happy to hang out through the afternoon. If there's any questions, I would like to acknowledge our dedicated staff here at Albuquerque for their hard work, especially during these really critical periods. Ann Tillery with the GS has been instrumental with helping us as well. And I've worked with Ann for close to a decade now. And then I'd like to also acknowledge our former Sue Deirdre Kahn, who was also instrumental in a lot of our early efforts. So my email's at the bottom. And with that, I will turn it back to you, Nick.
Thanks, Kerry. We have Amin already here, so we'll go ahead and give it to him. There is one question in the chat on YouTube if you want to log into that and answer that. But we'll go ahead and get Amin started. He is from the University of Texas. We're going to move it from New Mexico and go to the coast now. And so, Amin, feel free to go ahead and start.
I'm trying to find how to share my screen here. Oh, really? Okay, now I see that. Okay. So can you see my screen now? Okay. Good afternoon, everyone. My name is Amin Kiagadi, and I'm basically a joint appointed postdoc between University of Texas at Austin and University of Houston. Before I start my talk about compound flooding, I want to give credits to my co-workers and colleagues. So specifically Dr. Dawson and Mark, who did a lot for this project. So my talk today would be around compound flooding, and I'm going to start with defining the terminology and then go how this compound flooding can cause a lot of pain when you're trying to model severe storms and hurricanes. According to the IPCC, compound events defined as whether two or more extreme events occurring at the same time, or and next to each other, or when you have one extreme event with underlying condition that amplify the effect of the extreme event, or some events that by themselves or individually they're not extreme, but when they combine together they have an extreme event. But today, more specifically, we want to focus on compound flooding, and basically when you have both storm surge and rainfall at the same time. So in that scenario, you can see if you don't consider flow in your modeling, you will get the black hydrograph, and then once you consider the extra water from the rainfall or from the generated runoff, you can see that that can cause a larger peak, also a longer inundation and longer flooding in your system. And why this is important? Because traditionally, when we use the storm surge models like ATSURG or Delft3D or SLOSH, we don't consider the rainfall or the runoff from the watersheds. Or when we consider the HEC-RAS modeling for the inland flooding, that model by itself doesn't have the capability of covering a big domain or basically generating the storm surge within the model, and it basically can only be used for hindcasting, not for predicting or real-time modeling. So an example of compound flooding was Hurricane Ike in Houston in 2008. It was a Category 2 hurricane, landed on September 13 at 2 a.m. in Galveston. It caused a 5.3 meters storm surge in Galveston Bay and 4.3 meters storm surge in Houston Ship Channel, but also up to 40 centimeters of rainfall in some areas, specifically in White Oak Bayou, followed by that storm surge. So as you can see here, we had some storms, we have some rainfall, and then we have this storm surge. So these two effects together could amplify the effect of the surge in flooding of some certain areas. To be more specific, there are two specific research questions that I want to cover today. The first one is, what is the effect of riverine flow during a compound flooding? In other words, what would happen if you consider the flow in your model versus when you don't consider the flow? The second one is how the interaction among different watersheds could affect the water surface elevation. So this is very important when you're working with a smaller domain model like HEC-RAS or EFTC, when you don't consider all the watersheds that are next or adjacent to each other, but they can definitely affect the tailing water, and they can affect the water receptor water surface elevation, which basically can then affect your water surface elevation within the watershed. Today, I'm going to focus on Neches River watershed, which is like basically at the border of Texas and Louisiana. And this is Neches River, and this is Sabine River. I will talk about the studied area in more details momentarily. So in general, when we are talking about modeling compound flooding, we are talking about three separate systems: the hydrologic system, the hydraulic system, which could be a river or it could be like an estuarine system, and the ocean, the coastal surge system or the ocean system. Normally, the existing models cover one or two out of these three systems. But as of now, there is no model that can cover all three at the same time. So we have to couple different numerical models in order to simulate compound flooding. So right here at the boundary condition of each of these systems, we need to do the coupling. There are three different ways to do this coupling. The first one is one-way loose coupling. In other words, you run one model, you use the results of that model as the boundary condition of the second model, and then you run the second model. The two-way loose coupling is you run the first model, you put the boundary condition in the second model, you run the second model, you put the get the results of that second model, put it back in the first model, and then you do it back and forth several times up to the point that your results converge and you're happy with your results. The most difficult one is dynamic coupling, when you basically at each time step these two models talk to each other and then they converge to the point that, you know, with a small error that you decide. The challenge with that would be, for example, one of the models is written in Fortran, the other one is in Python or is in MATLAB. So it's really challenging to do that. Today, I'm only going to cover the first one, the one-way loose coupling, which is the most common way of coupling. And I will use in a way that we use the hydraulic model, and then we coupled it with the ocean model. So in other words, in this modeling framework, flow would be coming as the boundary condition, or riverine flow would be the boundary condition from one model to the second model. And the first model would be HEC-RAS 2D model, which has the capability of getting the rainfall as a direct input, distributed over the numerical mesh, and then put it in the river, and then bring it to the point that we want, which basically for Neches River would be here, and for the Sabine River would be here. Inside the AdCirc advanced circulation model that is capable of getting the so we got the flow from HEC-RAS, and then we tried different compound scenarios, but today I'm going to only talk about Harvey. And then there were some technicalities involved in this work. We had to develop a lot of new tools to be able to make these two models to talk to each other, and then make the data in a way that each of them accept in the right format. So as you can see, the black lines shows the domain of HEC-RAS existing HEC-RAS models, two separate HEC-RAS models developed by Army Corps of Engineers, one for Sabine, one for Neches River. And then it's a part of the Sabine to Galveston, or S2G project. We got the AdCirc mesh from the U.S. Army Corps of Engineers. That mesh contained more than 1.5 million nodes. And for the hydrodynamic scenarios, we looked at the Hurricane Harvey. One scenario was no flow. The other one was both Sabine River and Neches River. And the other one was just Neches, to see what would be the effect of Neches on Sabine River, basically, to kind of investigate the interaction among watersheds. So this is the run for Harvey. On the top right, you can see Hurricane Harvey with no flow. On the bottom of it is Hurricane Harvey with flow. And this one just shows the velocity field and the track of the Hurricane Harvey. So by the passage of the time, you can see in the top video, you have some inundation that you don't see it in the bottom one. But after a while, when the riverine flows start to come, you can see how much extra inundation happens in this area downstream of Sabine and Neches River due to inland flooding. So in the top one, what happened was, in the absence of the riverine flow, which is in the opposite force of the storm surge, basically that the storm surge propagated to the land. But in the bottom one, which was with the flow at the beginning, because of that riverine flow, basically they cancel out each other, so no inundation happened. But once the massive amount of runoff just came to the system, then you could see the effect of inundation. So this figure kind of showed the maximum elevation at each computational node, but please keep that in mind that this is not the real case scenario. This is, one cell could happen at the middle of the simulation, the other one could be at the end of the simulation. In other words, this is just shows the maximum elevation at each of the cells over the period of simulation. But you can see easily, you can compare flow versus no flow, where you can see the downstream of the Neches, downstream of the Sabine, and then like in the east part of the Sabine Lake, how much of difference in inundation and in the water depths or water surface elevation happened just due to the riverine flow. Normally, in a classic way that people use AdCirc, they don't consider these two inputs, and that could cause some problem. So moving to the just Neches only and then both rivers, You can see the basically at the beginning they act very similar to each other, but once the flow kicks in, you can see the Neches River is going down, and then after with a lag, the Sabine River comes in to the system and cause like a lot of more inundation in the east part of the Sabine Lake, which you don't see it in the with only Neches River. But that's not the only interesting thing. The presence of this Sabine River also caused some changes in the water surface elevation behavior within Neches watershed that I'm going to talk in the next slides. So again, looking at the max elevations, you can see within the Neches, the max elevation was not that different. Of course, in the Sabine was different because this one doesn't have the Sabine River inflow, but also here downstream and the east side of the Sabine Lake, it was huge difference. So looking at the, this is again Neches River, Sabine River, and then these are some locations that we looked at them. So if you look at the Neches River at the Beaumont, which is basically kind of at the top or the upstream of the AdCirc mesh, when we put the flow boundary over there, you can see the difference between both rivers and just one river and no flow is huge. So in other words, because right here at the confluence of these two rivers, there were like a lot of water coming up because of the Sabine River. That caused a significant backflow here all the way to this Neches River at Beaumont. That Beaumont at Yacht Club here, that difference is not that much. That the Sabine Lake, the difference here, like at the middle of the Sabine Lake, the difference is huge because this one is getting more water from the Sabine River. Here at the Rainbow, right here, again the difference, the one with both rivers had higher water surface velocity because again there's this back water over there. But right here at the mouth of Gulf of Mexico, the difference was not that much. And that's basically because even though this was a huge event with regards to the amount or the volume of the runoff came to the system, Gulf of Mexico has a lot of water, and then when you do that comparison, it didn't cause that much of difference in elevating the water surface elevation. In conclusion, AdCirc showed great capacity in including rivering flow and simulating compound flooding, and significant effect of local flow on land inundation. And then lastly, the interaction among watersheds could play a significant role in modeling compound flooding. And this is really important finding because when you're trying to model a watershed in isolation, and then you're not going to consider the amount of water that's going to go to the same water receptor as your watershed, then you can potentially introduce a lot of error to your model. So when you're using HEC-RAS or when you're using or HSPF or whatever other watershed management or hydro
Yeah, not sure what happened. I mean, if you can hear me, your mic stopped working like in the last 10 seconds of your conclusion. But we were able to hear 99% of your presentation and so forth. Thanks for that. Again, if you can hear me, hopefully you can. I think that was a really good presentation, a little change up from New Mexico, but some good data of how different rivers can interact with one another, especially with those heavy impact rainfall events like with Hurricane Harvey. So thanks again, and feel free to drop off. Looks like Dr. Nielsen Gammon has joined us. And Dr. NG, feel free to take over. And I think he left too. I think I'm by myself. There he is. Dr. NG, are you there? Dr. NG. Well, he may be having some technical difficulties, or it could be me. We'll try to double check real quick.
Hello there. I'm Audrey's coast. Okay, no problem. I'm just here to, in case there's questions Audrey would like to defer to me. Otherwise, I'm just going to kick back. Okay. So I can just leave it on mute unless you need me to log off. Okay. Because I'll probably just be on mute unless there's questions that she wants to defer to me. All right. Very good. Hey, I see John. John, it's Pat Fitzpatrick.
How you doing, Pat?
Well,
All right.
our stream should be working now. If Dr. NG can hear us, try to log back in, and we'll get him up and going.
Okay. John, I'll talk with you another time. I know you're busy.
All right. Good talking to you, Pat. Take care.
I'm at Texas A&M.
If Sharon Sullivan's watching, why don't you go ahead and get in the Google Meet, and we'll go to you and see if we can get Dr. Nielsen Gammon after.
All right, let's see.
All right, not sure what happened there, but we'll go ahead and go on to Sharon Sullivan with NWS Albuquerque. Hopefully Dr. Nielsen Gammon can join us a little bit later. But Sharon, go ahead and take it over.
All right, thank you. Good afternoon. For those of you who don't know me, I'm Sharon Sullivan, and I'm a meteorologist here at the Albuquerque Weather Forecast Office. In this topic, the 1941 Project, an extreme annual precipitation anomaly in the pre-radio sun era, we'll explore a year that has been so instrumental for the weather history of New Mexico. So this is a graph of annual average values for New Mexico. What stands out the most about this? Wettest year by a huge margin for the state of New Mexico was the year 1941, when a statewide annual average of approximately 26 inches fell, as compared to the average of approximately 14 inches. The extraordinary magnitude and persistence of this extreme event allowed us to assess possible climatic causes through a wide variety of historical records and analysis tools, including sea surface temperature anomalies, SSTs, synoptic scale composites, and external factors such as El Niño Southern Oscillation Indices over various spatial and temporal extents. So the questions we're trying to answer: could it happen again? Is it a one-time event, or is it predictable? The overarching goal of this project is to explain why the 1941 precipitation anomaly was nearly twice the seasonal average for the state of New Mexico. So I looked at the annual precipitation total by climate regions for the southwestern United States, encompassing Utah, Colorado, Arizona, New Mexico, and Texas, to determine the severity and area of this anomaly. And this was expressed as a percentage of the 20th century annual average for these climate divisions, ranging from 100 to 300% of normal. It seems it's more pronounced across New Mexico, more variability across Arizona, and seems to affect western Texas, but not the eastern portion of the state. And while it's not shown here, the northeastern region of the United States received below normal precipitation, and this result alone could suggest the possibility of an El Niño event. And if you look at our 4 locations plotted here on the map labeled A through D, 9 out of 12 months for these 4 climate sites exceeded their long-term monthly climate means. To put this year in perspective, Elephant Butte, a lake in southern New Mexico, just north of Las Cruces, was filled to its capacity for the lightning and one from hypothermia. It was also the 1941 Texas hurricane, which was the second named Atlantic storm of the season and causing $132 million in present-day amounts of severe damage. On an annual scale for some of our Texas sites, El Paso received 16 inches compared to the normal of approximately 10. Amarillo, 37, 20 inches is the normal. Lubbock, a little over 40 inches, while the normal is a little over 19 inches. So while you may be familiar with an El Nino event, where waters in the equatorial Pacific are warmer than normal, and the storm track shifts southward in North America, and this is typically characterized by a 5 consecutive 3-month running mean of sea surface temperature anomalies above or below the threshold, positive or minus half a degree Celsius. Using this Nino 3.4 region here in the middle, it's one of the most commonly used regions as it encompasses the western half of the equatorial cold tongue region and provides a relatively good measure of sea surface temperature changes and gradients. You may not be as familiar with PDO, or positive decadal oscillation, where sea surface temperatures are anomalously cool in the northern Pacific, the Aleutian low shifts southward, and warm, humid air is evected along the North American coast. This typically leads to winter precipitation that is higher than normal in Mexico and the southwestern United States. So this leads us to the question, was it the chicken or the egg? Did ENSO influence PDO, or did PDO influence ENSO to create this large precipitation anomaly? Because while El Nino is associated with higher than normal precipitation for New Mexico during the cool season months of winter and spring, the combination of a positive PDO and a moderate to strong El Nino can certainly enhance this relationship. So how do we analyze 1941? Recall that we did not have the advantage of upper air data, satellite, radar, so a determination of this anomalous pattern was difficult. In particular, we made extensive use of a new large-scale data set generated from a 20th century reanalysis created by the Earth Systems Research Laboratory. Essentially, the reanalysis uses historical surface data assimilated by a modern general atmospheric circulation model and yielding reconstructed 3-dimensional weather information for an era in which there were no direct upper air measurements. If we look at an example here from the 20th century reanalysis, we have our May and September composites, which were the 2 wettest months of 1941. So our May anomaly features a high pressure with a southerly flow of moisture from the Gulf of Mexico, and our September anomalies show strong forcings from a low pressure with moist southwest flow from the Pacific. But what's abnormal about these 2 months in particular is the strong persistence and moisture tap, tipping the scale for abnormal precipitation, but overall lacking that consistent ENSO-PDO signal and New Mexico precipitation across our summer and autumn months. We'll take a look at our 4 wettest storm periods of 1941. Our May 1st through 5th featured a closed upper level low over West Texas and southeast New Mexico with moist southeast flow. Our May 21st through 25th with high pressure over northern Colorado, a low over southern California, and a possible backdoor cold front into eastern New Mexico. The September 27th through 29th featured a surface high over South Dakota with an advancing cold front southeastward toward New Mexico. And our September 20th through 23rd, if we look here to the right, an example from our 20th century reanalysis, this period was characterized by remnants from an Eastern Pacific tropical cyclone. In addition, our 1941 monsoon season was ranked as the 20th highest total rainfall for the period running from mid-June through September, with a total of 5.44 inches, most of which fell in July, followed by 1.85 inches during September 1941. In an expansion of this project, I analyzed historical Mexican meteorological sites to look for other regional and global correlations in this 1941 precipitation anomaly. In Mexico, ENSO events not only affect winter precipitation, but also summer precipitation, reducing convective activity and rainfall across Mexico's central highlands, which is more critical for farmers. This effect is noticeable from sites such as Acapulco to Guanajuato to Puebla, while Veracruz remains slightly above normal. So the only other year that comes close to the 1941 PDO anomaly was that of 1987, with an annual average PDO index of 1.82. This year was also coupled with a Nino 3.4 index of 1.95. So if we take a look at these 2 years and their values, they're relatively comparable. But as far as 1941, it blew it out of the water as far as precipitation, still even twice that of 1987. So could these combined and unique climate patterns be used to signal future high-impact events across New Mexico and help forecasters become aware of potentially heavy rainfall periods? So I know this is a busy graph right here. So we have 1941 in the blue, 1987 in green, and all of these years are the top combined PDO and ENSO years, all of which are associated with heavy precipitation. But for 1941 in particular, we notice that our autumn precipitation is far outside of that of comparable years, and even exceeding in black here our upper and lower tercile boundaries for the 20th century. And as far as our late spring through autumn period here, it does not conform to the typical peak sea surface temperature variance and overall lacks that strong and consistent ENSO PDO signal during the summer months. In conclusion, a widespread precipitation anomaly such that occurred in 1941 is a low probability event based on the severity and area of the anomaly that was generated. The annual anomaly can be partially explained by external forcing, but unforced weather events are also added to this extreme anomaly. And while we have a combined positive PDO and ENSO here, not all events will be created equally. The combined PDO and strong El Nino in this case may not entirely explain the high precipitation values for 1941, but could have contributed to multiple independent high precipitation storm events region-wide, as the pattern is consistent with an El Nino event. But the difficulty in attributing this extreme annual anomaly to any specific climatic cause is a reminder that the pre-radiosonde era only provides a limited sample of natural climatic variability. And I'd like to thank Dr. David Gutzler, Dr. Deirdre Kahn, formerly of National Weather Service Albuquerque, and the forecasters from my office for their contributions and guidance throughout this research project. And with that, I'll go ahead and take any other questions. Thank you.
Thanks, Sharon. We just had one question in the chat.
Yeah.
I'll just ask it really quick since it seems like it'll be a short answer. Do you know if there was more rain gauges in 1941 now or versus now? Which had more rain gauges?
It seems like there is more data available now. I mean, there are certain climate sites that they did have back then that they've had to merge a little bit also, some of the ThreatX data. But I mean, that's as far as we have is some of the observations from like the NOAA guidebooks and like just personal observations. So that's kind of the main extent of it. So without the reanalysis, it kind of ties everything together.
Okay, thanks, Sharon. That was a really good presentation. We're going to move on to Audrey Flores from Texas A&M Corpus Christi. And then I did get a hold of Dr. Nielsen Gammon, and he's going to jump in after that one. I really think the problem was with the Google Meet software. Once I rebooted the Google Meet, things worked well. So maybe we hit their time limit. Something to know for tomorrow. But Audrey, if you want to go ahead and share your screen and get started, you can have it.
Can you see my screen okay? Oh. It's grayed out. Okay, can you hear me okay? Okay. Thank you, ladies and gentlemen, for allowing me to speak with all of y'all this afternoon. My name is Audrey Flores, and I'm from Texas A&M Corpus Christi. And I was going to present my research that I have been working with Dr. Fitzpatrick. He's my mentor. He's also from Texas A&M University, Corpus Christi. And this research actually got started about a year ago. When he and I first met, you know, we had a conversation and in his office, and he was telling me about how he was very interested in hurricane research, and I was telling him that I wanted to get into that as well. And during the course of the conversation, he brought up the rocket storm, and I told him I've never heard of that, and he said, you know, well, have you seen the picture? And I said, no, I haven't. And he said, well, come and take a look. And he showed me the picture, and I said, no, research this, but I haven't had the time, but I haven't found much on it, but why don't you take a crack at it and let me know what you think? And, you know, kind of be like a challenge. And so here we are 1 year later, and we're ready to present the rocket storm of 1954, the evidence for inclusion into HERDAT-2. Now, the purpose of our research was to substantiate that the landfall tropical disturbance that occurred in Brownsville, Texas on October the 4th of 1954 was likely a tropical depression. Our research is culminated in 3 separate parts. First is our introduction, where we're going to tell you a little bit about the storm, where it occurred, where it made landfall, and the criteria that's needed to be included into HERDAT-2. Our methodology is composed of 3 separate parts. We talk about the synoptic history of the storm and how it formed, the meteorological statistics and all the ground observations that were taken at the time that this event occurred, and then we apply the Dvorak technique to figure out where, you know, what the current intensity of this storm was at the time that it occurred. And then at the end, we will present our results. Okay, so what does a tropical depression need to have in order to be considered, you know, to be included into HERDAT-2? Well, first, it needs to have a close circulation with a defined center. And then the second thing, the storm must possess a warm core and have organized thunderstorms. And then third, it must originate in the tropics in subtropical waters, and it must possess sustained winds greater than 34 knots or 39 miles per hour. The synoptic history of the storm, we believe, formed in the Gulf of Mexico just north of the Yucatan Peninsula in Mexico. And we believe that it formed on October 2nd, 1954. The next day, it was determined that it had a sea level pressure reading of 1,010 millibars, and that would have been the very next day. Now, this map here shows it's a synoptic weather map, and it shows the low, as you can see here in the Gulf of Mexico. So you can see that it has formed. It's got a close circulation, and it's again in the Gulf of Mexico, just north of the Yucatan Peninsula. And then this map here, which is a sea level map, also shows that it has a 1,010 millibar reading again on October the 3rd, 1954. But what I also want to bring to your attention in this map is the frontal systems that you have coming down from the north. And this is going to play a really important role later on in the presentation. Now, what was going on the ground in Brownsville, Texas the day before? Well, it was pretty much a usual day. The pressure was reading at 1,013.5 millibars, and that was early in the morning. The temperature was 74, and then it got into a high of 90 around 1. But what was really interesting about the data was that we were looking at the wind, and we could see that it was increasing throughout the day, but it was also changing direction as well. It started in the east-southeast, then it flipped to the north-northeast. And then again, it began to increase throughout the day and then into the evening. By the next day, the pressure reading was very low. It actually got down to 1,006.8 millibars, and that was in the morning at 6 a.m. But you notice that the temperature didn't get above 80. But if you also look at the winds, again, it's actually shifting around. It starts out from the west, and then it ends and then coming out of the north-northeast. But throughout the day, it's shifting from the west to the south-southeast, back to the northeast. But you can also see you have a rainfall total that day of 6.67 inches of rain. Now, what's important to remember is that when this storm made landfall, it makes landfall around 4 in the morning. So from 4 in the morning to very close to 7 in the morning, it's raining continuously. You have very, very heavy rainfalls. So this 6.6 inches actually came, really all at once. And then, of course, it came into this one area and it really flooded out, a lot of the city. So, and it also flooded out a lot of cities in the valley as well. So to kind of get an idea of how the tropical storm or how the tropical rainfall with this storm proceeded to traverse not only the South Texas region, but also all of West Texas and into New Mexico, is we went through the data and we actually pulled out a lot of precipitation data for all these different cities. We put it in a CSV. We plotted it all using ArcGIS Pro. And but what we could tell is that we could see a very narrow path of the cities along the Texas-Mexican border where this storm really went through, and it's dropping its rain in a very, very tight area. So what was interesting is that as it traverses through, it actually gets quite wide. The area gets wider. The umbrella begins to really spread out for the precipitation. And once you get past Langtree, Texas, which is right about here, you can really see how the precipitation really begins to expand and really encompass a much larger area. But the heaviest rainfall actually ends up in New Mexico in a city called Canton. And the reason for that is because that frontal system that you saw in the previous map, they actually meet right here with the disturbance coming in from off the Gulf, and they meet right here. And Canton gets a record, if I'm not mistaken, about 10 inches of rain, which is quite a lot for that area. Okay, another thing that we also looked at that we were very interested in is we wanted to know, well, was there any wave observations that were made when this storm occurred? And remarkably, we were able to find some data. In the Corpus Christi Caller, which is a local paper here in my city, they actually printed an article that talked about a oil rig about 8 miles to the east of Port Aransas out in the Gulf, and they reported a 12 to 14 foot wave, or 12 to 14 foot waves that were coming in. And so my professor, Dr. Fitzpatrick, used that data, and with some iteration of parametric wave equations, he was actually able to work through, and he was able to ascertain that through these equations that this storm possessed anywhere from 35 to 40 mile per hour winds. So that certainly does substantiate that we probably had a really good tropical depression and possibly even a tropical storm. Now, this storm probably could have been a tropical storm offshore, but then as it moved towards the coast, it probably began to diminish. So again, going back to our story, where he actually showed me a picture of the storm as it was seen, he said it was taken by a rocket, and so I wanted to know what this rocket looked like. And after talking to an archivist over at the White Sands Missile Range Museum, they determined that this photo that you see of the rocket is probably what ours would have looked like. Our model actually was a very, very early model of the Aerobee rocket that was by the U.S. Navy, and it had a length of about 7.9 meters. And the launch time that it had took place at 13:15 Central Standard Time on the date of October the 5th, 1954. Now remember, our storm made landfall the day before, and this rocket takes off in New Mexico, in White Sands, New Mexico. But what was really cool about this rocket is that it had 2 cameras that were mounted on it, and one took pictures in black and white, and the other camera had a filter on it, so it actually could take photos in color, and this is what it looked like. This is the picture of the storm. This is the picture in color that was published in Life magazine on September 5th, 1955. So all of America got to see what the storm near the vicinity of Del Rio, Texas looked like. And so you can kind of see that it's, you know, it's a mass of clouds, and it's really cool looking. And I just thought it was great that we were able to find a picture of that in color. And so we decided, okay, so we've got a picture, we've got the wave, evidence, and we've got other ground observations. So now let's apply the Dvorak technique and see where we're at. So as we know, the Dvorak spiral is subdivided into 10 different sections. It's overlaid on the storm. The sections are counted, and of course, the current intensity is then determined. And this is the chart that we use. It should be no surprises to what it looks like. It should be familiar to everyone. A 1 on the scale is a tropical depression, and an 8 is a category 5 tropical cyclone. The only thing that I added that was a little bit different was I did add the maximum sustained winds in miles per hour. But this is what we used. Now, again, I do apologize. This is a photograph of the same photograph that we just saw previously, but this one's in black and white. And this is the Dvorak spiral. I tried to overlay so you can kind of get the idea. We overlaid it over the hurricane to kind of get an assessment of what we could determine what the current intensity of this storm would have been. And when we overlaid it, we think it probably got anywhere from 0.2 to 0.4 of the sections. So we believe that the current intensity would have been anywhere from a 2.0 to a 2.5, with a pressure reading of 1,005 to 1,009 hectopascals, with winds anywhere from 25 to 30 knots. Other evidence that we used was what we found online, and we found out that the U.S. Navy actually flew 3 flights into this disturbance. And from these flights, they also noticed that it had a close circulation, but it didn't have the gale force winds that would be required. But on the 2nd of October, they also said that one of the reconnaissance that went in got a reading of 1,006 millibars for this storm. So we thought that was actually pretty interesting, and it was also a very good clue as to what we were hoping to find. Because this map here from the daily weather maps actually shows this closed circulation pattern here that looks like it's centered in the vicinity of Laredo, Texas, and it's 1,008 millibars. So we know that out here was probably 1,010, probably closer to land. It was probably 1,006. It was probably very close to 1,006 here also in Texas. And from other research that I've looked at, in this vicinity here is where Del Rio, Texas is located. This is where when the rocket launched, this is the vicinity in which the storm would have been. And Laughlin Air Force Base recorded 1,009 millibars at the time that the storm had hit their area, but the airport actually reported 1,010. So it was beginning to weaken at this time. And again, remember, this is the area also too where the storm is beginning to spread out. Again, that precipitation umbrella is actually starting to take up much more area as it's heading into New Mexico. So here are our results. You know, last night we had my professor, Dr. Fitzpatrick, and I had a conversation. Does this storm check the criteria? Does it check all the boxes that it would need to be included? So the first thing we asked, does it have a closed circulation? Yes, it does. Does this storm originate in the tropic? Yes, it does. Does this storm possess a warm core with organized convection? Yes, it does. However, does it have sustained winds greater than 34 knots, 30 or 39 miles per hour? Undetermined at this time. Is this a tropical depression? Yes, we believe that it is. Could it have been a tropical storm? Undetermined again at this time. We are still combing through the data and trying to decide or trying to determine if in fact it was a tropical storm. But yes, pretty much for tropical depression, absolutely yes. And again, looking in the overall scheme, I know what a lot of y'all are asking as you're sitting in your offices or you're sitting at home and you're attending the conference. Well, what does this all mean in the overall arching theme of meteorology? Well, we're hoping that this research actually contributes to the reanalysis data for HERDAT-2 so that it can include this tropical depression. Remarkably, for all the evidence that's out there, this storm actually is not in HERDAT 2. It has not been included, but we're hoping that this research will, because again, in the overall scheme of things, as an atmospheric scientist or studying hurricanes, not just in the Pacific, but also in the Gulf of Mexico and in the Atlantic, we're hoping that by filling in the gaps that exist within that history, we can get a better assessment as to what has happened in the past. It's hard to understand what you're seeing now. Forget about what you could see in the future if you can't see or understand or get a full understanding what happened yesterday. And so that's the culmination of our work, and that's what we're hoping to accomplish with our research. So with that, these are our citations that we use, and you can see it was quite a lot, but thank you so much for sending the research. We really do appreciate it. NWS in Corpus Christi, Miss Melissa Huffman helped us out a lot. Louis Stoke and Alliances for Minority Participation Program, who really supports our research. Jen Jett, museum specialist at the White Sands Missile Range in New Mexico, who sent us the photograph and information about the rocket. That was really great. And also the library staff at the Mary and Jeff Bell Library. And with that, I will take any questions.
No questions, just one comment that they really enjoyed the historical presentations. It's like forensic weather detective doing these. So just wish you good luck in getting that into the database. That was a very interesting presentation, and we thank you for bringing it to us.
Oh, great. Well, thank you for having me, and we really appreciate it.
All right, we're going to try to get Dr. NG in. Let's see if it works. Can you test out your microphone? Oh no. Let me try him one more time. Well, we'll give it one more minute, but we may have to push it till tomorrow. All right, I'll touch base with him tomorrow, and we'll go ahead and end the conference for today. Thanks everybody for joining us. Sorry about that little hiccup there with him. We will go ahead and end the conference for today. Tomorrow we start off with lightning at 8 o'clock sharp. There's no introduction, so we'll get started at 8 o'clock, and we'll try to fit Dr. NG into one of the breaks. 30-minute break's probably a little excessive, so we should be able to squeeze that in. And go from there. So thanks everybody for joining us today. Again, if you need any continuing education credits, please just send us an email and let us know. And with that, we will see you all tomorrow.